Good afternoon. Welcome to the live streaming of Intergroup 2020 pre-recorded sessions. Prior apologies for mispronunciation, if any. The talks covered under the segment encryption are Adaptively Secure Threshold Symmetric Encryption by Pratay Mukherjee, Vetted Encryption by Martha Norber and Martin Stamm, Security of Public Encryption Against Resetting Attacks by Juliana Kramer, Patrick Struck.
Hello everybody, welcome to my talk. I am Pratay Mukherjee from Visa Research. I'm going to give a talk on adaptively secure threshold symmetric encryption. So the story starts with a very simple question that how to store sensitive data. If you Google that, then the first thing that pops up is encrypted data. It's wonderful, but slightly more detail, what it exactly does is basically it reduces the storage requirement from big data to small keys. So earlier you needed to store a large amount of data, and instead now you encrypt all your data, but now you need to store the encryption key. So the next question that comes up is how to store the key. Okay, so one naive approach could be that you encrypt your data and store a ciphertext on some server and store the secret key on a separate server. Although this is a nice solution, it suffers from an obvious attack like single point of failure. For example, if an adversary breaches into the server where the secret key is stored, then it can basically decrypt all the data ever encrypted with that particular secret key. So typically in industry, what people does is basically use a hardware security module which stores the secret key, and then whenever the decryption is needed, the hardware security module can throw out the secret key and decryption is performed. Although it has a lot of benefits, there are some obvious drawbacks of these solutions. Like for example, there are a lot of side channel attacks for these kind of solutions. Secondly, there is a lack of flexibility. That means HSMs are typically bound to some particular algorithms, and it's very hard to make any change to them. And then HSMs of good quality, as you can see here from the Google search, that the cost can vary from like $40 to several $100,000. So because of the high cost of a good quality of HSM, sometimes it's very expensive. So here we are not going to talk about hardware-based solutions. Rather, we focus on to software-based solutions. So in software-based solutions, there is solutions like provided by Vault, which basically does a secret sharing of the secret key. So it chooses different servers to store the shares of the secret key. Let's just consider the secret key split into two parts, SK1 and SK2. It's a very simple 2 out of 2 secret sharing. And then whenever decryption is performed, the secret key is gathered to one server, and then it is reconstructed and the decryption is performed. So the problem with this kind of solution is that it requires reconstruction during decryption. So if you want to decrypt again and again very frequently, then it leaves the secret key on memory for a long time. And due to this exposition, it sort of suffers from this kind of attack. Is called snapshot attacks, where the adversary can breach onto the server on this particular moment, take a snapshot, and can acquire the secret key. So that becomes a big security issue. So basically, we are looking for solutions where we want only software-only solutions, but without any reconstruction of the secret key. So the first thing that comes into a cryptographer's mind is use techniques like general multi-party computations, where you can think about the server storing the secret key like SK1, SK2, the shares, and then they interact to compute this following function that's decrypt on this XOR of this SK1 and SK2, and then output the decrypted value. There is a line of work that actually does this kind of approach, where mostly they do MPC of the AES. So one particular good point of this solution is that it can compute any scheme. For example, AES, which is a standard encryption schemes, and then it can comply to standard. But there are several other drawbacks of this solution. For example, it's not a scalable solutions because it's either highly interactive, that efficient MPC algorithms takes basically much more than 2 rounds. There are optimal MPC solutions that takes exactly 2 rounds, but often they are very inefficient. They rely on tools like fully homomorphic encryption or something similar. Also, they are kind of bandwidth intensive because typically all the servers need to talk to each other. So the overall communication cost become order of n square. And furthermore, MPC solutions typically works with Boolean circuits. So if you want to use MPC for like say AES decryption, first you need to convert AES to a Boolean circuit, equivalent Boolean circuit, and that will lead to a lot of blow up in the computations. So overall, although there are certain benefits like complying to standards and like flexibility of using any scheme, it suffers from severe efficiency issues. So in 2018, a paper called Distributed Symmetric Encryption, or DISE, it's my work along with Agrawal, Mohasel, and Rindal. And we proposed this solution that basically formally defined this problem of distributed or threshold symmetric encryption. So in this paper, we defined threshold symmetric encryption via intuitive game-based definitions, and we achieve security like privacy and authenticity. So it basically works like a distributed version of authenticated encryption, and it works up to T-1 malicious corruption. We proposed a generic construction in that paper, and that's based on any distributed pseudorandom function in some sort of black box manner. And our solution only required 2 rounds of communication, which is basically round optimal. The responders don't interact. That means the communication is basically order of n. And there are several implementations that was done in the paper. It's instantiated with 2 different DPRF constructions. So both of them actually are basically first proposed by Naur, Pincus, and Reingold in 1999. One of them is based on public key operations and reduces to DDH assumptions, and another is like just from PRF-based solution but has some sort of limitation. However, one drawback of this solution is that in that paper only consider static corruptions. Whereas this work, we actually consider adaptive threshold symmetric encryption. So what we did is we augmented the security definition from DISE, like formally defined adaptive threshold symmetric encryption. And we have again like privacy and authenticity both for malicious but adaptive corruptions. Our construction is actually exactly same as DISE. So we do not propose any new construction, but we showed that if DISE construction can be instantiated with any adaptively secure DPRF in a black box manner, that actually achieves our definition. So we formally proved that in this paper. So we instantiated with a augmented version of DDH-based DPRF using this idea from this work by Libe, Joe, and Jung. Their work actually worked for adaptive threshold signature. We incorporated ideas from that paper and augmented the NPR's DDH-based DPRF to an adaptive setting. So additionally, for a stronger definition, we also require adaptive non-interactive zero knowledge. And for that, we propose a simple construction random oracle model. Furthermore, we showed that the PRF-based DPRF construction that was also used in DISE is actually kind of optimally secure in the adaptive setting. So in this talk, we will be focusing mostly on these particular adaptive DPRF-based constructions, and we'll briefly talk about why the PRF-based DPRF is also optimal. So in the rest of the talk, first, I'll be briefly describing the intuitions of adaptive versus static security. And then I'll be talking about NPR's DDH-based DPRF construction and why their proof actually do not work with adaptive corruption. Then I'll be talking about our DDH-based DPRF construction that uses ideas from LJY. I'll give proof intuitions, and finally I'll briefly talk about why NPR's PRF-based DPRF constructions is actually optimal in adaptive setting. Okay, so let's talk about adaptive and static security. So what happens in static security is that there are parties, and parties are basically corrupt at the very beginning of the security game or the execution. So once the parties are corrupt, then the protocol starts executing by rounds after rounds and so on. Whereas the adaptive setting, as its name suggests, parties gets corrupt at sort of any point of time, and it becomes strictly stronger than static security because at this point the corrupt party can take part in some interactions. It gathers some information from this round one interaction, and based on that it can decide to corrupt either of the two parties that's depicted here. For example, based on this interaction, it decides to corrupt this party, and then it can again take part on the further interaction. It can basically dynamically corrupt any number of parties as long as the total number of corruptions stays within the limit. So in this case, we consider a threshold T, so the total number of corruptions will stay below T at all time. So slightly more formally, in the proof of static security, the simulator gets to know the set of corrupt parties in the beginning, but in the adaptive security, that doesn't happen. So that's why it's kind of challenging to prove anything in the adaptive corruption setting. Okay, so now let me talk about NPR's DDH-based DPRF construction. So the construction is as simple as that, taking a hash of the input and raising it to the power of the key K. And when you're in distributed setting, then the K is basically secret shared. So here let's consider a very simple example where 3 out of 3 setting. So K is basically additive secret sharing of K1, K2, and K3. So party 1 will have K1, party 2 has K2, and party 3 has K3. So on input X, each party will do a partial evaluation, which is basically very similar to the final evaluation. Instead of like raising to the power of the whole key, they raise to the power of their part of the key. So in particular, party 1 does hx to the K1, party 2 does hx to the K2, party 3 does hx to the K3, and so on. And then on receiving the partial evaluations, y1, y2, and y3, they can be combined simply just by multiplicating in this case, and that will lead to the output of the DPRF as the exponent will be added. So now in the proof, the goal is to show that DPRF X is pseudorandom as long as DDH holds, but the difference from the standard PRF setting or the non-interactive setting is that this should hold even if the some number of parties are corrupt. So let's consider this reduction, which has the DDH tuple G to the A, G to the B, and G to the C. So what happens in the proof is that it implicitly sets the value A, let's say A, to the key K, right? So it's implicit. That means that it does not exactly know the value A or K, right? But it implicitly somehow uses that. So now the adversary corrupts parties like party 1 and party 2 in this case. And once the reduction knows the corrupt set, and that's why you're using the fact that this is a static corruption. So then the rest of the sort of simulation is kind of simple. It can just choose random K1 and K2, and that still leaves the entire K undefined because it does not know K3, right? So it can know K1 and K2 and give them back to the corrupt parties, and then can use the K3 as sort of the unknown factor and can simulate the entire game. So that's the basically overall idea of the pseudo-randomness proof of this DPRF construction. Now it's not too hard to see why this fails in the adaptive case, because this is very crucial that it knows the corrupt set, right? So what happens in the adaptive case is that the corrupt set is unknown. So let's try to see what happens if it executes the exactly same steps. So let's say the adaptive corruption happens for the party 1 first. So it chooses random k1, k2, and define again k3 is equal to a minus k1 minus k2, and this is like implicit definition. However, now the adaptive party decides to corrupt party 3 instead of party 2, right? So the reduction can give k1 to the party, but now the reduction does not know k3. So then that becomes a problem. It cannot really simulate this corruption, right? So that's why basically the proof fails. And in fact, slightly more detail, what exactly happens is that it's choosing this k1 and k2 randomly. So it's basically it's guessing the corrupt set ahead of time, and in this case that turned out to be wrong, right? So now if you are in the case of t out of n, and then if every time reduction needs to guess the corrupt set, then that's bad, right? Because then the possible number of corrupt set is like in the order of n choose t, and if t is like somewhere in the middle, so of course if t is constant, this n choose t is like not a big number, but if t is somewhere in the middle, like over 2, then n choose t becomes like exponential. So the reduction will only be successful with negligible probability. So that's why the proof does not work for adaptive case. So let's see how we can fix it. So we take the idea from LJY, adaptive threshold signature. So what we do is, instead of having exactly one key, now we have sort of two parts to the key, like parts U and V, and we use two basically random oracles, hx to the U and g to the g of x to the v, and the rest of the schemes is basically exactly the same. So U and V are secret share. So this should not be like XOR, that's a typo, sorry about that, and it should be like a plus. And then everybody computes their evaluations, like partial evaluations, and the combinations is exactly the same, right? So now let me briefly talk about the main idea of the proof. So the main idea is that reduction always knows entire key U and V, and hence it can actually give correct key shares for adaptive corruptions. It's kind of simple to imagine that if the reduction always has the key, right? So earlier we saw the reduction does not know the entire key because it sort of uses the DDH exponent as its key. So in this case, if the reduction can know the entire key, then it becomes basically trivial to simulate. But we have to make sure that that becomes consistent with the other information the adversary gets. And for that, we use random oracle programming in such a way that adversary does not have enough information about K from the other parts. So basically K has enough entropy, and that sort of we leverage in the proof. Okay, so let me briefly talk about the hybrids that we use in the proof. So the real game is kind of simple, and we just show that how the real game simulates the random oracle queries, because then in the next hybrid we'll change that. So random oracle query on any x or any xi is simulated as hxi equal to g to the ri, and gxi is equal to g to the si for random ri and si. That's kind of a standard simulation technique. You choose a random exponent and raise to the power of the generator. However, in the first hybrid, we do it slightly differently, that we choose a W, which is random, and instead of choosing Ri and Si randomly, now we program Hxi is equal to G to the Ri and Gxi is equal to G to the Wri. And note that this W stays the same for all Xi queries. So for Xj, it will be G to the Rj and G to the Wrj, right? So the W becomes common in these two cases. And it's not too hard to see that these two experiments are basically computationally indistinguishable as long as DDH holds, because we basically making this change in the exponent, and you can simulate this via just plugging in that actual DTH value. And since we're not changing anything like the actual keys and everything, so this is like completely independent of the keys K, right? So then the entire rest of the experiment can be simulated perfectly. The reduction knows the key K, so everything goes smoothly. So what happens in the next hybrid is we'll be changing how the eval queries are responded. So in hybrid 1, the eval queries are responded correctly. For example, eval x is responded with hx to the uj. This is for party j. That's why the index j times gx to the vj. So in hybrid 2, this is quite different, that eval x is responded with g to the zj, where zj is basically a random value, right? So z is basically a random key and zj is its share, and it's responded with this particular value. And now why this is okay to do, because note that what happens in the eval case here is eval of x is become hx to the uj times gx to the vj. So according to the simulation, it becomes like g to the this quantity, like ri times uj plus w times vj, right? So now this is like a universal hash functions, as long as u and v are basically randomly chosen, and they are the key of the hash functions. R and w are the inputs, right? And since it's like a universal hash functions and it's statistically close to a random value z, it's okay to instead just sample a key zj and just exponentiate to the generator. And that's why these two experiments are statistically indistinguishable. So now interesting to see that eval queries are actually completely independent of the actual key k, right? So now at this point, the reduction can always know the key k and simulate the eval queries independently. And whenever a corruption query from the adaptive corruption comes up, it can send the corresponding key to that party. That's how the simulation is possible. Now, this is a very high level overview of this proof technique, but this actually really simplifies the entire proof. So compared to the DISE DPRF proof that as done in the CCS 18 paper, this proof is much simpler because of this particular adaptivity feature. So now let me briefly talk about the PRF-based DPRF construction and why it's optimal even in the adaptive setting. So here let's consider 2 out of 3 threshold, because otherwise it's a little bit hard to explain. So in the 2 out of 3 case, the DPRF is basically PRF of K1 and PRF of K2 and PRF of K3 and XOR of all of them, right? And the key K is consists of different PRF keys like K1, K2, and K3. And parties are distributed the keys such a way that any two party will have all the keys. So in this case, it's kind of simple that first party will have the first two keys and second party will have K2 and K3 and last party will have K3 and K. Like the partial evaluation is kind of simple. It evaluates the PRF on the inputs on K1 and on input K2 and so on. On receiving all these values, it basically chooses the correct value, and that's the output of DPRF. So now if there are like t out of n parties, if t is the threshold and it's somewhere in the middle, the efficiency scales with n choose t. So now, since the efficiency already scales with n choose t, now we saw that the reduction can always guess the now corrupt set with a loss of 1 over n choose t. So that basically adds a one more constant factor, and that's why it's basically already adaptively secure by this simple guessing technique. So finally, summarizing that, we have defined and constructed adaptive threshold symmetric encryption in this paper. We instantiated with a new adaptive DPRF, and it suffered from about 2x slowdown compared to DISE, which is a pretty good trade-off to get a much better like adaptive security. The adaptive DPRF proof is conceptually much simpler than the static one, and it's particularly more prominent for the malicious corruption. So you also provide a stronger adaptive DSE we did not have time to talk about, but that requires a adaptive zero-knowledge proof, non-interactive zero-knowledge proof for a specific commit and proof statement in the random oracle model. As a future work, we can think about removing random oracle without compromising efficiency for this particular TSC scheme. With that, I conclude my talk. Thanks a lot for paying attention.
Hi, my name is Martha, and this is the presentation of the article Vetted Encryption, written in collaboration with Martijn Stam for INDCrypt 2020. And we'll start off the presentation with the definition of vet, which is to appraise, verify, or check for accuracy, authenticity, etc. In our scenario, a sender is vetted in order to send confidential messages to a particular recipient, and whether a sender is vetted or not is publicly verifiable, although we don't use a list for this. Instead, when a sender is vetted, they're given an encryption key that they can then use to encrypt messages. And the verification of vetting is then checking that the ciphertext has been constructed using such a vetted key. Now, there's similarities to filtering, and one can envision a third party between the sender and the recipient doing the recipient's bidding, where the filter ensures that only messages originating from vetted senders make it on through to the recipient. And this can describe many different scenarios. For example, spam filters for email, but also making sure that only registered users are allowed to post on a bulletin board. So one aspect of this, which is important, is whether or not a sender is identifiable to the filtering party. And we propose primitives for both scenarios. So in the case where the filter knows the identity of the sender, it's covered by identifiable vetted encryption, or IVE for short. In the case where the filter doesn't know the identity, it's covered by opaque vetted encryption, OVE. And there's similarities to other primitives for both cases. So for IVE, there's similarities to identity-based encryption, wherein two parties that are identifiable to each other can send each other confidential messages. However, typically for identity-based encryption, you don't have the notion of public verifiability because it runs counter to other security notions for encryption. And when you do, the verification relies on a interaction between the verifier and the recipient. And this doesn't really match the use case for IVE, or OVE for that matter, where we envision that the recipient sets up the filter once and then doesn't need to interact with it any further to determine whether a particular sender is vetted or not. For OVE, there's similarities to group signatures. Group signatures allows one to determine whether or not a member of a group has signed a message. But in order to pinpoint exactly which member has actually signed the message, one needs a particular opening key that's typically reserved for the group manager. Now, group signatures are signatures, so they don't really have a notion of confidentiality associated to them, or message recovery, which is something we need for OVE. However, because of the other similarities, we are inspired by group signatures when we construct our own OVE scheme. In particular, we're inspired by the BMW construction. So, given this brief introduction, we can now dive into IVE first. And for IVE, there's the following structure. There's a key generation algorithm, a derivation, encryption, verification, and decryption algorithm as well. The decryption, the key generation, produces both a public key and a secret key. The public key is given as input to the encryption and verification algorithm, and the secret key is given as input to the derivation and decryption. Derivation algorithm always takes as input the identity and uses this to derive a encryption key for a user, which is then used to encrypt messages. Now note that the identity is given as an explicit input to both the verification and decryption algorithm. So given this basic structure, we can start building the security notions that we require for this scheme. And we start with the notion of integrity, which is based on the following game. So the adversary is given the public key of the IVE scheme. She's also given access to a derivation oracle, seen on the left-hand side, where she queries an identity and gets a handle H in return. She may use this handle to either corrupt the identity by querying her corruption oracle and getting the encryption key back, or she can use the handle to encrypt messages under identities where she doesn't have the encryption key, using the encryption oracle on the lower left side. She's also given access to a decryption oracle. Now, the challenge for the adversary, given all these aids, is that she should output a tuple of an identity and a ciphertext, so that the identity is uncorrupted and the ciphertext has not been returned to her from the encryption oracle, and also that the ciphertext verifies under the identity she has specified. And for an IVE scheme to achieve integrity, this challenge should indeed be hard for an adversary. And this captures the notion that it shouldn't be possible to bypass the filter, that the only way to actually have a ciphertext which verifies is to be a vetted sender. We also have the notion of confidentiality for IVE schemes, which is similar to the notion of confidentiality for public key encryption schemes. Here, the adversary is given the public key of the IVE scheme. Now, because the secret key is used for decryption purposes, we obviously can't give it to the adversary directly, but she still needs to derive encryption keys, and for this purpose we give her the derivation oracle seen on the upper right corner. She's also given access to a decryption oracle, and she queries her cipher oracle, challenge oracle, with an identity, encryption key, and two messages M0, M1, and she's given the encryption of one of them. And her challenge is to distinguish between encryptions of M0 and M1. And now, as is the case for encryption schemes, this captures the notion that ciphertext shouldn't leak any information about the underlying plaintext. So a naive approach to construct an IVE would be to combine an identity-based signature scheme and a public key encryption scheme in an encrypt and sign construction. However, the problem with this is that you don't achieve confidentiality, because in this case the challenge ciphertext is just a tuple of a encryption of a message alongside a signature of that encryption. But in this case, the encryption key is just a signing key, which the adversary has, and she can then just re-sign the encryption to achieve a new tuple, which is a valid query to her decryption oracle. And in this case, she will trivially win the game. So what we need is unicity of signatures, as well as an identity-based signature. So as far as we know, such a primitive has not been suggested previously, so we do suggest it in the literature, and the way we achieve this is using the standard certificate-based transformation for a signature scheme, wherein the key generation is de-randomized, so the randomness used to derive signing key and verification key is dependent on the identity using a PRF. So it's shown that when using this construction on a signature scheme, one achieves an identity-based signature scheme. So we just apply this same transformation on a unique signature scheme. And in addition to the normal security notions for identity-based signature schemes, we also insist on outsider unicity of a UIBSS, where the adversary is given the verification key and also a derivation oracle, and she should output a tuple of an identity, a message, and two signatures, where both signatures should verify on the message and identity, but they should not be equal. Now, we do allow for distinct signatures on messages, but we insist that finding a pair of distinct signatures that verify should be difficult for an adversary here. And now, given this building block, we can construct an IVE using an encrypted sign. So the key generation of the IVE is just the key generations of a public key encryption scheme and a unique identity-based signature scheme. The public key of the IVE is the public keys of the underlying schemes, and the same with the secret key. The derivation is just the derivation of the underlying signature scheme. For encryption, we encrypt the concatenation of the message and the identity. The reason we concatenate the identity at the end is to link the encryption directly to an identity, which we will use during decryption. Then we sign the ciphertext and return the tuple. Verification is just the verification of the signature scheme. For decryption, we decrypt C and then pass it as MID, and then we check that the concatenated identity matches the one given as input to the decryption algorithm before we output M. Now, integrity follows quite easily from the unforgeability of the signature scheme, and confidentiality follows from the confidentiality of the underlying public key encryption scheme, as well as the outsider unicity of the signature scheme. And that covers IVE, and we can move on to OVE, which has a similar structure as IVE. So there's a key generation, derivation, encryption, verification, and decryption here as well. Though note that the identity is here the output of the decryption key, not input. Another difference is that key generation outputs not one but two secret keys, an issuing key and a decryption key. But here as well, the issuing key is given as input to derive alongside the identity, which outputs a user encryption key, which is then used to encrypt messages. And as was the case for IVE, we now use this to build up security notions for these schemes. And we start with the integrity, which states that any adversary with access to all the keys of the scheme has to output a ciphertext C. And the winning condition for this game is that the ciphertext should verify, but also output a invalid message or identity. So for an OVE to have integrity, it should be difficult for anyone to output a ciphertext which passes the filter but then opens to something nonsensical. So being able to do this means that you will be able to essentially spam the recipient with either a nonsensical message, or you wouldn't be able to pinpoint who sent the message, which is not a desirable quality. We also have privacy, and here we give the adversary access to both the public key and the issuing key. And we can do this because we've split the properties of the secret key into both issuing and decryption. So the adversary is here able to derive any encryption key she chooses. She also has access to a decryption oracle here. Now she sends EK0, EK1, M0, M1 to her challenge oracle that answers with the encryption of one message under the corresponding encryption key. And here as well, she should be able to distinguish between M0 and M1 encryptions of them in order to win the game. Now this reduces to confidentiality if the encryption keys are the same, but it also reduces to anonymity if the messages are the same. And we give a explicit proof of this in the full article. And here as well, the intuition is that ciphertext shouldn't leak any information about the content of the plaintext, but also who sent it, unless one is in possession of the secret key. Finally, we have the notion of traceability, which is a security notion from group signatures. Here, the adversary is given the public key of the encryption scheme, or the OVE scheme. And here as well, she has a derivation oracle that she can query identities and get a handle. She can use this to corrupt the identity by getting the encryption key, but she can also use it to encrypt messages for identities where she doesn't have the encryption key. And here as well, she has a decryption oracle. The challenge of the adversary is then to output a ciphertext, so it hasn't been given to her by the encryption oracle. It's not under a corrupted identity, and also that the verification accepts the ciphertext. The intuition here is that an adversary shouldn't be able to impersonate anyone, so that even a vetted sender is not able to produce a ciphertext which opens to a different identity. Now we can move on to constructions that achieve this, and again we're inspired by the B&W construction for group signatures. So the key generation is just a key generation of a public key encryption scheme, a signature scheme, and a NISC. The public key of the OVE is the public keys of the underlying schemes. The decryption key is the decryption key of the public key encryption scheme, and the issuing key is the signing key of the signature scheme. So here the derivation is just producing a certificate, a signature on a particular identity. The encryption is the encryption of the using the encryption scheme on a concatenation of the message, certificate, and identity under a randomness R. We then use all these four components to produce a proof showing that the sender does indeed know all the components that went into producing the ciphertext C. Verification is then the regular verification of the NISC, and for decryption we decrypt using the encryption scheme and then parse the result as the message and identity, which is the output. So as for IVE, the security notions follow quite readily from the properties of the underlying schemes, but for full proof and also all the details for the constructions, you can check the article, full version, which is now available on ePrint. There you will also find more on background and references and so on. Thank you for watching.
Welcome to the presentation of the paper Security of Public Key Encryption Against Resetting Attacks. My name is Patrick Struck and this is joint work with Juliane Krämer. In this work we're looking into public key encryption. So we have two communicating parties, Alice and Bob. When Alice wants to send over some message to Bob, she will use Bob's public key to encrypt the message using the encryption algorithm and then send over the ciphertext to Bob. And then Bob uses the corresponding secret key to decrypt the ciphertext and then get the message of Alice. Then in between we have the adversary who will see the ciphertext that Alice sends over to Bob. And we deem such a scheme secure if the adversary does not learn anything about the underlying message M from the ciphertext C. A standard security notion for public key encryption scheme is indistinguishability under chosen plaintext attack. In this security notion, the adversary gets the public key as an input, and then it gets oracle access to a challenge oracle, which also gets the public key and some secret bit B as input. The adversary can then invoke this oracle on two messages, a left and a right message. The oracle will, depending on this bit B, pick either the left or the right message, encrypt it to get the ciphertext, and then send the ciphertext back to the adversary. And after many queries, the adversary then is supposed to output a bit B prime as its guess for the bit B. And the adversary then wins if it guesses the bit B correctly. Now in this notion, the randomness here is implicit in the encryption algorithm when the challenge oracle encrypts the message. If we rewrite this to explicit randomness, we have the same setting with the adversary and the oracle. Now if the adversary sends two messages, the oracle will first generate the random coins Ri for the ith query of the adversary, and then deterministically produce the ciphertext by encrypting either the left or the right message using this generated random coins, and then send back the ciphertext to the adversary. Now, a crucial part for this notion is that these random coins are generated independently for every query of the adversary. And main question is, what happens if this is actually not the case? There are different flavors of what can go wrong with the randomness used during encryption. In this work, we are considering the scenario mentioned by Garfinkel and Rosenblum, as well as considered by Ristenpart and Jilek. So they have the setting where the randomness is obtained from the current state of a system. And if we use virtual machines, then they can create a snapshot of such a security critical state from which the randomness is then derived. And this entails that if such a snapshot is then restored, then this would result in a reusing of the randomness. This gave rise to the resetting attack model proposed by Jilek in 2010, which is a strengthening of the INDCPA security notion seen on the last slide. So here we have the adversary, and it gets some target public key PK star as an input. The adversary has then access to some challenge oracle, which also receives the target public key, a challenge bit B, and some random coins R star as an input. The adversary can invoke this oracle on two messages, and the oracle will pick, depending on the bit B, either the left or the right message of the adversary, and encrypt it under this target public key and these random coins R star, and then send back the ciphertext to the adversary. In addition, the adversary gets another learning oracle, which receives also this random coins R star as an input. This oracle can be invoked by the adversary on some public key and a message. The oracle will encrypt the message under the public key queried by the adversary using the random coins that it receives as an input, and then send the ciphertext back to the adversary. In the end, again, the adversary outputs a guess B prime for this challenge bit B and wins the game if it guessed the bit correctly. Now, there are some queries which are forbidden in this security notion because this would result in trivial wins for the adversary. So, for instance, the adversary is not allowed to make two queries to the challenge oracle which agree in one of the messages but differ in the other. So, for instance, if the adversary queries the message M0 and M1, it can then not later query the same message M0 together with a different message M2 to the challenge oracle. And the reason is quite simple, because clearly if the bit B is 0, then it will see the same ciphertext twice, while in the other case, since there were two different messages, M1 and M2, it will see different ciphertext. Furthermore, the adversary is not allowed to query message together with the target public key to its learning oracle if this message is also queried to the challenge oracle. As a separation between the INDCPA security notion and the resetting attacks, Jilek considers the hybrid encryption scheme, and concretely the instantiation of the hybrid encryption scheme using the one-time pad as the underlying symmetric key encryption scheme. So it will generate a key for the one-time pad encryption, which it will encrypt using the underlying public key encryption scheme, and then use the one-time pad to encrypt the actual message. Now, due to the fixed randomness in the resetting attack setting, this means that the same one-time pad key is used for every encryption. And for this, the adversary with one learning query to its learning oracle on an arbitrary message, the adversary can learn this one-time pad key, which will be used every time, and then use this key for decrypting the ciphertext part C2 of the challenge ciphertext. In this work, we extend this separation result by showing that not just this particular instantiation of the hybrid encryption scheme is insecure against resetting attacks, but in fact every instantiation is insecure. And for this we give the following attack. So if an adversary picks two messages, M0 and M1 at random, and invokes its challenge oracle on this message to get the ciphertext consisting of the two ciphertext components C1 and C2. It will then query the same two messages to its learning oracle on a different public key than the target public key. This is why this query is allowed, because it's not the target public key. And for these two queries, the adversary gets back the two ciphertext here. And it then can simply check for the second part of the ciphertext, so which of the two ciphertext it gets back from the learning queries, for which the second part equals the second part of its challenge ciphertext. And due to the deterministic encryption using the underlying symmetric encryption scheme, this will be equal for one of the two messages. And this then enables the adversary to perfectly distinguish the cases, whether the left or the right message was encrypted. We show that furthermore that some other schemes are insecure against resetting attacks, and this includes the canonical LWE-based encryption scheme due to RegF, and the code-based encryption schemes HQC, RQC, and Rollo2, which were submitted to the NIST post-quantum cryptography standardization process. Along with the security notion against resetting attacks, ILEC also proposed the simplified security notion, where the adversary is restricted to only one challenge query to its challenge oracle. This is a standard simplification for these INDCPA-like security notions. And the claim made is that security in this simple setting of a single challenge query implies security against an adversary making multiple queries to the challenge oracle, even for resetting attacks. And the given proof for this is via a standard hybrid argument. So this is the setting for the proof. So if an adversary, and in fact it tries to distinguish whether its challenge oracle is instantiated with the bit being 0 here on the left side and the bit being 1 here on the right side. Now ILEC proposed the following hybrid games GI, where in the game GI the first I queries are answered by encrypting the right message that the adversary queried, while the last Q-I queries are encrypted using the left message that the adversary queries. This means that the game G0, for this always the left message is encrypted, so this corresponds to the case of the oracle being instantiated with the bit B being 0, while GQ, all the message, for every query the right message is encrypted, which means this game corresponds to the oracle being instantiated with the 1, while all the other games are in between. And then ILEC proposed to you to do a hybrid argument over these games. So more technically, if we have an adversary that can distinguish two consecutive hybrids, the games GI minus 1 and GI, then we can construct an adversary which makes only a single challenge query against the resetting attack game. Now we have an adversary which makes here Q queries, always consisting of two messages. Now for the first I-1 queries, both games will respond by encrypting the right message that the adversary has queried. For the ith query, the game GI will return the ciphertext obtained by encrypting the left message that the adversary queried, while the game GI will return the ciphertext obtained by encrypting the right message of the adversary. And for all the remaining queries in both games, the left message that the adversary queried will be encrypted. So you can see the only difference in this game lies in the ith query, while all the other queries are answered the same. Now for the reduction, it will, except for the ith query, all the other queries will be answered by using the learning oracle from the resetting attack game. So for the first I-1 queries, the reduction will take the right message of the adversary and send it together with the target public key to its learning oracle and send the response back to the adversary. while for the last queries, it will pick the left message of the adversary together with the target public key and forwards it to the learning oracle, as well as the response back to the adversary. And then for the ith query, the reduction will take the challenge will take the two messages of the adversary and forward it as its own challenge to its own challenge oracle. And then depending on whether its challenge oracle on the bit of its own challenge oracle, it will either simulate game GI-1 or game GI for the adversary. So if the adversary can distinguish, so can the reduction by only making a single query to its challenge oracle. However, this proof was identified as flawed by Patterson, Schult, and Seaborn in 2014. And they observed that the reduction in fact makes a forbidden query. Now going into the problem of the proof. So let's consider the case that the adversary now for the ith query queries two messages M0 and M1 to its challenge oracle. For this query, this is the query that the reduction will forward, so it will also invoke its own challenge oracle on the message M0 and M1. Now, if the adversary for the I+1 query queries the message M1 and M0, so it just flips the order of the two messages to its challenge oracle, then this means that the reduction will query the target public key together with the left message, which is now the message M1, to its learning oracle. However, this query is forbidden because now the adversary queries a message to its learning oracle together with the public key, which it also queried at some point to its challenge oracle. So this raises the question whether this implication of security against an adversary making a single challenge query implies security against an adversary making multiple challenge queries holds also for the resetting attacks. In our work, we then show that the issue lies not in the given reduction, but instead it lies in the hybrid games. For this, we consider two types of special queries. The first one are flipping queries, which are essentially the one for which Patterson et al. Pointed out that the reduction does not go through. The other one being repeating queries where, well, as the name suggests, the adversary just makes the same query twice. And both of these queries are allowed in the security notion. Now, if we consider the two hybrid games, GI-1 and GI, we can consider we can give an adversary that can distinguish the games almost perfectly by making these queries. Now here we consider the flipping query. So we have an adversary, and for the ith query, it will query the messages M0 and M1, and for the following query, it will make a flipping query M1 and M0. Now in game GI-1, for both of these queries, it will be encrypted by taking the left message of the adversary. So the ciphertext CI will be the encryption of the message M0, and the ciphertext CI+1 will be the encryption of the message M1. And this means that the ciphertext will most likely be different. However, in the game GI, the ciphertext CI will be obtained by encrypting the right message, while the ciphertext CI+1 will be obtained by encrypting the left message. And this means that for both these ciphertexts, the message M1 will be encrypted. And this means that the ciphertext CI and CI+1 will be equal in this game. This means that these flipping queries allow the adversary to distinguish the two consecutive hybrid games, GI-1 and GI, almost perfectly. And the same argument also applies for the repeating queries, with the only difference that then the ciphertext will be equal in game GI-1 and different in the game GI. So this means that the proof approach cannot be fixed by changing just the reduction and how the reduction responds to the queries of the adversary. To restore the claim that the single challenge security implies multiple challenge security, we then give an alternative proof for the claim. And mainly we change the existing proof in two different ways. So first, we use two hybrid arguments instead of just one hybrid argument, which is essentially the part which solves the problem of the flipping queries. And second, for each of the two hybrid arguments, we only do the hybrid argument over the number of non-repeating queries by the adversary, which we denote by Q star, which solves the problem of the repeating queries. So we have the picture from before, so we have the adversary, which tries to distinguish the oracles being instantiated with a bit B being 0 or with a bit B being 1. And now in this proof, we consider some intermediate oracle, which just responds by encrypting random messages for every query. We then give some hybrid games Li, which work as follows. For the first I queries, it will encrypt a randomly chosen message, while for the remaining Q star minus I queries, it will encrypt the left message of the adversary. And whenever there's a repeating query by the adversary, it will just output the same response as the first time this query was made. For these hybrid games, it holds that L0 corresponds to the challenge oracle being instantiated with a bit B being 0, while LQ star corresponds to this intermediate oracle, which just returns the encryption of randomly chosen messages to the adversary. Similarly, we define games Ri, where the first I queries are answered by encrypting also a random message, and the remaining Q star minus I queries are answered by encrypting the right message of the adversary, and likewise repeating queries are just answered by repeating the response. And for this, it also holds that game R0 corresponds to the challenge oracle being instantiated with the secret bit B being 1, while RQ star corresponds to this intermediate oracle by just returning random messages. And in fact, the two games LQ star and RQ star are in fact equal. For this, we can then do the two hybrid arguments. So the first hybrid argument is which we do over the hybrid games Li, and the second hybrid argument over the hybrid games I. How does this look like for the games Li? So we have an adversary which makes these Q star non-repeating queries to its challenge oracle. And now for both games Li-1 and Li, the first I-1 queries will be answered by just picking a random message and encrypting this message under the random coins R star. For the ith query in game Li-1, the left message of the adversary will be encrypted, while for game Li, also a random message will be chosen, which then will be encrypted. And for all the remaining queries in both games, the left message gets encrypted. So again, we have that the only difference lies in the response of the ith query for the adversary. And we then still have that reduction now for every other query except the ith query will respond with the learning oracle. So for the first I-1 queries, the reduction will simply pick a message at random and invoke its learning oracle on this message and send the response back to the adversary. And for the query I+1 up to the query Q star, it will simply pick the left message of the adversary, forward it to its own learning oracle, and send the response back to the adversary. And for the ith query, the reduction will forward the query of the adversary to its own challenge oracle as the response back to the adversary. Now the main difference is now for the ith query, where the adversary queries the message M0I and M1I, the reduction does not invoke its challenge oracle on the message M1I, because it invokes it on the message M0I and a randomly chosen message. This enables then the reduction to be later able to query the message M1I to its learning oracle if the adversary makes a flipping query. And a very similar argument applies to the other hybrid games I. Now if we look at the adversary, let's consider the case of this flipping query. So if the adversary, and for the ith query, it invokes the oracle on M0 and M1, and for the following query on the flipping query M1, M0. And for the first one, the reduction will then take the left message M0 together with a random message and invoke its own oracle, its own challenge oracle on these two messages. And now for the second one, it will pick the left message of the adversary, which is the message M1, together with the target public key and forwards it to its learning oracle. But now this query is valid because the adversary never queried the message M1 to its challenge oracle. And with this, we can show that the security against a single challenge also implies security against multiple challenges, even for the resetting attacks. And in comparison to the claim made by Jilek in 2010, we only get an additional factor of 2, which stems from the fact that we use 2 hybrid arguments compared to 1 hybrid argument. To wrap up, in this work we studied the resetting attack model proposed by Jilek. And we showed that many schemes are susceptible to resetting attacks by showing that they are insecure with respect to the security notion. We then show that the single challenge security in fact implies multiple challenge security even for the resetting attacks. For this, we showed that the original proof approach does not work, and then we give an alternative proof for the claim. This concludes my presentation. Thank you very much.
The talks covered under ciphers and cryptanalysis are Cryptanalysis of the Permutation-Based Algorithm, SPOC, by Lilia Kraleva, Raluca Postoka, and Vincent Riemann. More Glimpses of the RC4 Internal State Array by Pranab Chakraborty and Submoy Maitra. Mixture Integral Attacks on Reduced Round AES with a Known or Secret S-Box by Lorenzo Grassi and Marcus Schonegger. Counting Active S-Boxes is Not Enough by R. Renkelman et al.
Hello everyone, it is a pleasure for me to present at INDCPA this year, and thank you for watching my presentation. I'll talk about the cryptanalysis of the permutation-based algorithm SPOC, which is a joint work with Raluca Posteluca and Vincent Riemann. We focused our attention on the cipher SPOC, which is a second-round candidate to the NIST Lightweight competition, which started at 2019. The competition aims at standardizing a portfolio of lightweight algorithms with a focus on authenticated encryption schemes and hash functions. The security requirements are at least 112 bits of security, and the ciphers need to satisfy certain criteria for performance. Currently, the competition is on its second round with 32 ciphers left, and the third round candidates would be announced at the end of this month. In this work, we constructed round-reduced differential characteristics for the SLY SCP-Lite permutation, which is the permutation used in SPOC. Then, using these characteristics, we present tag forgery attacks on both SPOC versions. Furthermore, a key recovery attack on SPOC 64, regardless of the permutation, and a message recovery attack based on the characteristics are presented. Finally, some observations on the constants used in the permutation are given. My presentation will continue as follows. I will first introduce the algorithm of SPOC and the concept of differential cryptanalysis. Then I will show our differential characteristics of the permutation and how we use them for the tag forgery attacks. Further, I will present the message and key recoveries on SPOC 64 and finally the observations on the constants used in the permutation. This is a diagram of the mode of operation of SPOC. SPOC is a sponge construction and therefore the state is divided into rate and capacity bits. The authors introduce masked capacity bits, which is where the message and associated data are added. The mode of operation consists of the following phases: initialization, associated data processing, message processing, and tag generation. The initialization is the only part that is different for the two SPOC versions. Here you can see the initialization for SPOC 64. After loading the key and half of the knowns to the state, the permutation is applied and then the second half of the knowns is added. For SPOC 128, this phase consists only of loading the key and the knowns to the state. The associated data and message processing phases are very similar. After each block is absorbed to the state, a control signal is added to the rate part. The value of this constant depends on the phase and the length of the block. The ciphertext is then obtained from the message processing phase by XORing the message and the rate bits. The permutation used in SPOC is the SLY-SCP light permutation. The left figure shows one step of this permutation. First, the state is divided into 4 equal subblocks. Then a S-box layer is applied to half of the state and a constant is added to the other half of the state. Finally, the subblocks are permuted. The S-box used in the permutation is the Symme cipher with a constant instead of a key. And the round of the Symme cipher is shown at the left. For completeness, I am listing the parameters for both SPOC versions and the corresponding permutations. Note that both versions of SPOC use 128 bits key and nonce with different rate and tag size. For the permutation, we have different size of the S-box and different number of Symme rounds, while the permutation steps are the same. This table summarizes the security claims of the authors. As we interpreted them, the best attack on either version of SPOC should use at most 2 to the 50 data encrypted under the same key and has a time complexity of at most 2 to the 112. Furthermore, the attack aiming at either breaking the confidentiality or the integrity of the cipher should have a success probability of at least 2 to the minus 16. At first sight, it seems that all our attacks have complexity more than 2 to the 50 data. However, our attacks use different keys and therefore the restrictions are satisfied. Differential cryptanalysis is one of the most powerful and used cryptanalysis techniques against symmetric primitives. The basic idea is to take two plaintext with a difference only in few bits and follow how this difference propagates throughout the whole algorithm and the ciphertext. By taking the difference before and after each round, we define a differential characteristic as the sequence of all intermediate differences. If we assume that the rounds are independent and the keys are uniformly distributed, we can compute the expected differential probability of a characteristic by multiplying the single round's probabilities. However, in practice, we can often only observe the input and output differences, so we call the pair of input and output differences AB a differential. Generally, computing this probability is a very difficult task, since it is the sum of the probabilities of all possible characteristics with the same input and output mask. Therefore, what is done in practice is to bound this probability with the probability of the optimal characteristic. For our experiments, we used the SAT-solver-based tool ARXPy to search for optimal characteristics over the Symme S-box of the permutation in order to compute the differential probability of the S-box. Our differential characteristics are constructed over round-reduced versions of the permutation, and we impose some constraints on the input and output differences in order to use them later on for the attacks on SPOC. So the characteristics that I will show you are not the optimal ones in general, but the best ones for our attacks. This is our characteristic of the 256-bit version of the permutation. It covers 6 out of 18 rounds with 6 active S-boxes, and we have constraints only on the output difference, fixing the first and third subblocks to delta 1 and 0. The purpose and value of this delta 1 I will explain later. The difference in the other two subblocks is chosen in a way to minimize the active S-boxes at the last rounds. So in this way we have only 2 S-boxes in the last 3 rounds. In fact, the constrained first and third subblocks actually correspond to the rate bits of the cipher. The best probability we have for this characteristic is 2 to the power minus 106. To construct this characteristic, we use the ARXPy tool to find optimal characteristics of the S boxes and link the input and output masks. Then we empirically calculated the differential probabilities of the S boxes over the chosen differences in order to obtain the probability of the characteristic. Here you can see our 9-round characteristic of the 192-bit version of the permutation. It covers 9 out of 18 rounds with 8 active S boxes. Here we put constraints again on the output, but this time we fix the first and third subblocks to 0 and want a difference only on the second and the fourth subblocks. And these subblocks correspond to the capacity part of the cipher. The best probability we have is 2 to the power minus 109. Our tag forgery attacks are based on several observations on the algorithm of Spock. First, note that a no associated data or an empty message means that the corresponding phase is completely skipped. Furthermore, a different constant is added at each phase and depending on the block length. Finally, the initialization of Spock 128 consists only of loading the key and nonce to the state. Here you can see how the processing of only one block of message with no associated data would look like. And I'll try to give you the intuition behind our attack. Assume that we have a no associated data and two one-block messages, an incomplete block M and a complete block M star, which is the padded M. If we process the two messages under the same key nonce pair, then the only difference in the processing will be the different control signal that is added. If we manage to cancel that difference, then the internal states will be the same and therefore the produced tags would be equal. We looked for characteristics of the permutation such that the output difference in the rate part is the sum of those constants, and this is exactly the convenient difference delta 1 for which I talked about. In these figures, you can see the encryption process of the messages from the previous slide under the related key-related nonce pairs chosen in accordance to our characteristic. If our characteristic holds, then the output difference in the capacity will be cancelled by the difference in the messages, while the difference in the rate will be delta 1, which would be cancelled locally by our characteristic. Depending on the scenarios, we identified 3 possible values for the difference delta 1. The first one is the case of no associated data and 2 messages M and M star as I described. Then we have 2 cases of encrypting a no associated data and a message M and another pair of associated data, some associated data derived from M and empty message. In both, the second pair will produce no ciphertext, however, the tags will be the same and we can use that to forge the verification of the associated data. The tag forgery attack then goes as follows. With a key nonce pair, we ask for the encryption of a random, incomplete message block M and we obtain the ciphertext and the tag. Then we verify whether the differential over the last S box holds in order to filter out the ciphertext. Since we know the rate part from the message and the ciphertext, we can easily invert the S box and verify whether the input difference is the delta 2 that we expect. If the verification holds, we can continue by asking for the decryption of the ciphertext shown in step 2. under the related key nonce pair from the characteristic. If the verification does not hold, we change the key nonce pair and repeat. Note here that we can repeat every time with a different key. The attack on the other version of Spock is very similar to this one. However, it follows different scenario for Delta 1, and we forge the verification of the associated data. The data complexity of this attack corresponds to the probability of the characteristic and is 2 to the power 106. The time complexity is measured by SBOC calls instead of encryptions and is 2 to the power 107. We can improve these complexities by having multiple characteristics with the same output difference, delta 1, and in our paper we list some that are some characteristics that can be used. Furthermore, a time memory trade-off can be used by generating a table with all words satisfying the verification condition. And then instead of calling the inverse SBOX every time, we can have table lookups. Both our message and key recovery attacks are on Spock 64 and are based on the fact that for Spock 64, the initialization phase is not bijective, meaning that there exist multiple key nonce pairs leading to the same internal state. This happens because the size of the state is smaller than the size of the key and the nonce together. Based on that, we aim for a collision after the initialization phase, and we propose two ways to achieve a collision. Using the differential characteristic that I showed in the beginning, which we apply for the message recovery attack, or a time memory trade-off approach, which we use for our key recovery attack. Our message recovery uses the 9-round characteristic, which is constructed with the constraint to have output difference only in the capacity part. If the characteristic holds, then after the permutation in the initialization phase, the difference will be only in the capacity bits, and we can then cancel it with the addition of the second half of the nonce. After that, the encryption will be identical and the tags will be also the same. The attack goes as follows. With some key nonce pair, we ask for the encryption of an arbitrary unknown plain text and obtain the ciphertext tag pair. Then we ask for the decryption of this ciphertext under the related key related nonce pair that you can see on step 2. If the tag verification holds, we obtain a plaintext M', and if it is a readable text, then this is the recovered message. I say readable text here because there is always the probability due to the birthday paradox that the tags will collide. If the text is not readable, then we repeat from step 1. The data complexity of this attack is bounded by the probability of the characteristic and is 2 times 2 to the 109. For our key recovery attack, we would formalize things a little. We say that two key nonce pairs are equivalent or in the same equivalence class if the corresponding internal states after the initialization phase are equal. Since the size of the state is 192 bits, we have 2 to the 192 equivalence classes and 2 to the 64 key nonce pairs in each class. It is important to note that encrypting the same plaintext with equivalent pairs leads to the same ciphertext, and vice versa. Decrypting the same ciphertext with equivalent pairs gives the same plaintexts. Our key recovery attack consists of two phases, an offline and an online phase. For the offline phase, the adversary first chooses a commonly used message M. What is a commonly used message? Well, depending on the environment, in many scenarios, it happens that certain blocks occur often as the beginning of a message. For example, if we send an email, we normally start with dear or hello. So here we assume that such a message exists. Then 2 to the 110 key nonce pairs are generated such that they give different equivalence classes. Finally, a table with 2 to the 110 entries is generated, and in each entry are stored the key nonce pair and the corresponding ciphertext of the chosen message M encrypted under this key nonce pair and the null associated data. For the online phase, we intercept random messages encrypted by a valid user. The adversary then verifies if the first 3 blocks of the intercepted ciphertext belongs to the table. We choose 3 blocks because we believe this length is enough to ensure uniqueness. A match would mean that the adversary knows the internal state after the initialization, so to go backwards from this state, the adversary simply XORs with N1, which is the second half of the nonce, and then applies the inverse permutation to recover the initial state and the key. This table summarizes the online and offline complexities together with the total complexity of the attack. The total complexity has 2 to the 67 data, 2 to the 110 time, and 2 to the 110 table entries as a memory. Finally, I will show you an observation of the used constants. Those are the constants used in the permutation and the S boxes. We notice that even though the designers of SlySCP claim that the round and step constants are different, in fact some of them are equal. The constants are derived from an LFSR with length 7 and period of 127, which means in particular that the bit of RC0 and the ETH step is equal to the RC1 in the E plus 8 step of the permutation. Furthermore, you can see also that the first 3 pairs in the first table are equal to the last 3 pairs in the second table. We have not developed this further into attack, but we think it is an interesting observation. To conclude my talk, our attacks and their complexities are summarized in this table. Please note that even though we respect the security claims, our attacks are still theoretical and do not compromise the security of SPOC. However, our key recovery attack, which is the strongest scenario, is a generic attack, which implies that there might be a vulnerability to the mode of operation of SPOC. Thank you again for watching my presentation, and if you have any questions, you can always send them by email or ask them now. Thank you.
Hello everyone, good morning, good afternoon and good evening, depending on the time zone from which you are watching this. My name is Pranab and I'm going to talk about the paper titled More Glimpses of the RC4 Internal State Array. I am affiliated with Wipro Limited in its learning and development function. My work area is leadership development and my special interest of research lies in cryptology and digital contact tracing. My co-author, Professor Dr. Shubhamoy Moitra, is affiliated with Indian Statistical Institute. He works in the field of cryptology and quantum information. First, the outline of the talk. We would talk about the basics of stream cipher, followed by RC4's brief history, and then we will describe RC4 algorithm, and then we will talk about what we mean by the glimpse of RC4. In our results on glimpses, we would talk about 3 parts. First part will focus on further investigations over Jenkins glimpse. Second part will focus on effects of Flurer-Magru bias on new type of glimpse. In the third part, we will again come back to Jenkins glimpse, but we will look at the refinements of it from the perspective of Flurer-Magru bias. And then we will have our concluding remarks. First, the basics of stream cipher. In this particular diagram, as you can see that there are message bits and key stream bits and ciphertext bits. Now message bits, which is MI, is XORed with the key stream ZI, and when this XORing is done, you generate the ciphertext CI, and that CI, when you decrypt by XORing again the ZI stream, you get back MI. So it's a pretty simple and straightforward process. And if we look at from the two parties perspective, you have Alice as a sender and Bob as a receiver, or vice versa. And imagine Alice has to send a set of bits MI, which are the data and information bits from one end to the other. And the ZI bits are the key stream bits available with both Alice and Bob, where ZI is indexed with I equal to 0, 1 and so on. And while sending, Alice has to do the XORing with the ZI, and while receiving and decrypting, Bob has to do the XORing with the same ZI series to get back MI. Now, the background and the theory of this goes back to Shannon's well-known 1949 paper on information theoretic security. And from the perspective of information theoretic security, we know that ciphertext should not reveal any information about plain text. Now, if we look at an ideal implementation of ZI, we can think of one-time pad. What is one-time pad? Imagine Alice and Bob are sitting across a table and tossing an unbiased coin enough number of times to generate the key stream bits. And then they take a portion of the key stream bits and use that for encryption and decryption. But definitely this is not a practical, because Alice and Bob would never really sit across the table and have an access to an unbiased coin for this purpose. And because they will be situated and seated farther apart from each other, they will not have easy access to the common ZI. So in that case, how do we actually get hold of ZIs for the practical purpose? Now this is achieved by sharing a short length key, say 128 length key, if we have shared between Alice and Bob, and there is a deterministic algorithm which uses that key to generate a pseudo-random series of bits Z0, Z1, then those series of bits can be used by both to do this encryption and decryption. And since both of them have access to this key, which is initialized and which is used to do this particular generation of pseudo-random series, they will have the same set of Z bits or Z0, Z1 bits at both their ends. Now, let's talk about a brief history of RC4. RC4 is the most popular stream cipher. It was developed by Ron Rivest way back in 1987. When it was developed as a proprietary algorithm of RSA data security. But it got leaked in cypherpunks mailing list. The algorithm got leaked, and as an alleged RC4, it came to be known, which later on got confirmed that that is really the algorithm. And we'll talk about the algorithm soon. Now, as we know that RC4 is most widely deployed stream cipher, and in SSL, TLS, WEP, WPA, Apple Open Collaboration Environment, Microsoft Windows, Lotus Notes, Oracle Secure SQL. And as we can see, both in the public domain, in the internet, as well as in the organizations or with the product vendors, this particular cipher has been very widely used. So the deployment has been pretty vast, far and wide. Now, one of the interesting aspects of RC4 design is that it's just a 4 lines of code. And since it has this apparent simplicity, it has attracted various cryptanalytic attacks, and cryptologists all over the world, the stalwarts, have worked on it. And publications in crypto, Eurocrypt, AsiaCrypt, FSC, Journal of Cryptology, that means almost all top conferences and journals, RC4 research has been published. And through all these researches, all this cryptanalysis and a number of attacks, it has been shown that there are vulnerabilities in RC4. So as of now, the present status is IETF has published RFC 7465 to prohibit the use of RC4 in TLS. Google, Mozilla and Microsoft have issued similar recommendations, and it is believed that some of the state cryptologic agencies may possess the capability to break RC4 when used in the TLS protocol. However, since it was used all across in both public and private sector, and there are different legacy implementations where this is still present, it is not very easy for a complete replacement of RC4 all across. So the process is on, and it's also an interesting cipher to do many more cryptanalysis, and finding out interesting results is always, it gives us a lot of additional insights. Now RC4 description, if we have to describe RC4, it consists of an internal state array called S array or S box, which is of the length n, that is 256 bytes, and this is an array of unsigned characters. The secret key is of a length of 5 to 32 bytes in general, and there are two indices, I and J. I is called the sequential index and J is called the pseudo-random index. Now how is the key used? The key is expanded first, that is capital Ki is equal to small k I mod L. That means if you have K0 to KL minus 1 small k indices, that is expanded to fill the complete length of 256 bytes. That's how the capital K array is created. And then we come to the key scheduling algorithm part of RC4. So RC4 has got two parts, key scheduling algorithm and PRGA, pseudo random generation algorithm. Now if we look at this aspect of the initialization, we will find that the counter is initialized, J is initialized to 0, and then in a loop I equal to 0 to 255, J is changed, but it is changed using this particular formula, J equal to J plus Si plus Ki. That means the key is used to update J, and whenever you get the new J, Si and Sj is swapped, and this is done for all 256 rounds. And hence after this, the initialization that was done Si equal to I, that completely get changed, and that is the starting point of PRG algorithm. And we must note that all additions here that we are talking about is addition modulo n equals 256. Now in pseudo random generation algorithm, what is done is initialization of the counters, both I and J is done to 0. Then I is incremented sequentially, that is I equal to 1, I equal to 2, I equal to 3, like that it goes on. So I is equal to I plus 1, and J is incremented by J plus Si. So whatever is the value of Si, that is added to current J to get the new J, and then Si and Sj are swapped, and the output is found out by S of Si plus Sj. That is Si plus Sj gives a new index to the same S box array, and the output of that gives the key stream value of Z. That's how Zi is created, and as many number of Zis are required by the sender and receiver, that's how they keep on generating it. Now this is a pictorial representation of what we talked about just now. As you can see, S box is basically the array which is supposed to be not apparent or not visible by looking at Z values, because this is the internal state, and when I and J are there, I is sequentially incremented, so I values are known, but J is not known because J is incremented based on Si values, and Si plus Sj gives the new index value from which Z is calculated. If we look at the operation, you would have initially plaintext bytes, the stream of bytes called P, and you will generate through this RC4 operation Z bytes. and you will create the ciphertext byte C by doing XOR of P and Z. So P XOR Z gives you C, and similarly in the decryption end, C XOR Z will give you back P. Now interestingly, even though everything is looking so simple and 4 lines of code, but look at the state space. There are 256 bytes in the S box, right? And they can be arranged in any permutation possible, which is like 2 to the power 8 factorial, which if you multiply by the values of I and j, the possibilities for both of them is 2 to the power 8, you get a state space of 2 to the power 1700, which is really a mind-boggling number. Now interestingly, strength of RC4 relies on both KSA as well as on PRGA, both these parts. Now for this particular paper we will focus on PRGA. Now what is glimpse? What happens is, in a stream cipher, as we have said, that it is not desirable that information about the internal state would be revealed from the key stream. But way back in 1996, Robert Jenkins showed that RC4 cannot satisfy this, and we will show the result here. So we have the complete information about the public index I and the key stream byte Z at any round of RC4. The question is, from I and Z, is it possible to obtain additional information, that is glimpse, regarding the hidden variables J, Si or Sj other than the random association? You see, random association means it can be anything out of the n equal to 256 value, that is 1 by n is the probability. But can we get more than 1 by n probability? And Jenkins showed that yes, that is true, possible. So this is the theorem, the Jenkins glimpse theorem, where it is said that during RC4 PRGA for any arbitrary round R, probability of SIR equal to JR minus ZR is nearly 2 by n, which is 2 by n minus 1 by n square, and its dual, or you can say the complementary representation, which is probability of SR JR equal to IR minus ZR, is also similar, that is almost equal to 2 by n. So it is different from 1 by n, the random association. Now why does it happen? As you can see, if you fix, suppose, SR JR value to the value of ZR, if you do that, then you know that SRIR plus SRJR index has to point to that particular place of the array, which means that has to be same as JR. Now SRJR is equal to ZR. This forces the value of SRIR to be JR minus ZR, because if you add these two, ZR will cancel and JR will remain, and that's how ZR can be indexed from this. Now if you look at the possibility of probability of SRJR equal to ZR is 1 by n, that's the probability, right? And in this probability, this particular configuration happens with 1 probability, which is 1 by n multiplied by 1. And the remaining cases where this is not happening, that is SRJR is not equal to ZR, the probability by random association there you will assume at 1 minus 1 by n. For each of those cases, again, there is a 1 by n chance of the desired configuration, that is SRIR is equal to JR minus ZR to happen, right? Now if that is the case, then you see the last line of this particular slide, and there we have added both these things together, and as you can see that 1 by n times 1 plus 1 by n, 1 minus 1 by n times 1 by n gives back 2 by n minus 1 by n square, which is almost equal to 2 by n. That's how the result comes. Now we have come up with our contributions in this area by finding out that there are 3 categories of new randomness results that we can talk about. First is that using Jenkins glimpse result that we have showed just now, it is possible to find out that there is a correlation of key stream value that is coming from a distant permutation array of S-box byte position with a probability higher than fair chance. Now we will soon explain what we mean, and we will explain the proof also here. And not only that, moreover we show how the Jenkins glimpse gets modified when 2 consecutive output key stream bytes are equal to a certain value. This is also an interesting new result. We'll talk about this. Now this is the first corollary. As you can see that so far in Jenkins correlation or glimpse, you saw the involvement of JR. Now JR is a pseudo-random index which is not known upfront. So it is very difficult to use that particular glimpse result to arrive at an understanding of a value of a particular item in the S box, right, in the internal state array. But here we have proved a result where we can actually show that ZR value is equal to SR of ZR plus ZR plus 1, always with a higher probability. In some cases it is 1 by n plus 1 by n square, and in some cases it is 2 by n. Now there are two cases, and both these cases are conditioned by value of IR. Now IR is not equal to ZR plus 1 minus 1, the first one. Let's talk about this particular instance and let us show the proof here. So this first line, that IR equal to ZR plus 1 minus 1, suppose that is the situation we are considering. And now suppose we introduce a variable Q is equal to ZR plus 1. Now if IR is not equal to Q minus 1, this case, under usual randomness assumption, we can say that probability of JR plus 1 is equal to Q is 1 by n. Now this is one probability you keep in mind. Now as per glimpse theorem, again we know that probability of JR plus 1 minus ZR plus 1 is equal to SR plus 1 IR plus 1 with a 2 by n approximate probability. Now this particular thing we are taking the Jenkins result in the R plus 1 round, remember, right? Now JR plus 1 minus ZR plus 1 is equal to SR plus 1 IR plus 1 implies Q minus ZR plus 1, because we have already assumed JR plus 1 is Q. Q minus ZR plus 1 is equal to SR plus 1 IR plus 1, which is same as SRQ. Why? Because in the Rth round, whatever is the value of Q, now that moved into R plus 1 round in the place of IR plus 1. That's why we are writing this. Now here if we put the value of Q is equal to ZR plus 1, which we initially have assumed, we get that ZR is equal to SRQ, which is the desired condition. ZR is equal to SRQ. Q is ZR plus ZR plus 1. Now what is the probability? We have so far seen that 1 by n is the probability of JR plus 1 equal to Q, and in that case 1 by n times 2 by n square approximately is the probability that we get under this situation, right? Now there is a complementary situation where JR plus 1 is not equal to Q, right? And in that situation the probability is 1 minus 1 by n, and we consider a random association of 1 by n for the desired configuration. So essentially what we get is that we add these two, that is 2 by n square plus 1 minus 1 by n into 1 by n, which gives back 1 by n plus 1 by n square, and we have computationally also validated this particular result as has been explained in the paper. Now the other part where IR is equal to Q minus 1, that's also interesting, because as per Jenkins theorem, IR plus 1 minus ZR plus 1 is equal to SR plus 1 JR plus 1 is equal to SR IR plus 1, because IR plus 1 in the round of Rth round, in the R plus 1 round it goes to JR plus 1, right? Now that happens with a probability 2 by n. Now if we look at IR plus 1 minus ZR plus 1 is equal to SR IR plus 1 implies Q minus, because IR plus 1 is equal to Q, Q minus ZR plus 1 is equal to SRQ. That is, now if we put in the place of Q Z plus ZR plus 1, ZR plus 1 cancels out and we get ZR equal to SRQ, which is the desired result, and the probability, as we have already seen here, the probability is almost 2 by n. That's how we have proved a new result where the Jenkins glimpse is used to come out with a fact that the value of ZR in each round is related to the value of the byte in a S box in a particular location, which is indexed by ZR plus 1, right? Now the next result is also very interesting. We have seen that the Jenkins glimpse probability is 2 by n, right? Now, we are now showing that there are situations where this changes. Now, this is a situation where ZR and ZR plus 1 both are having a value, that is 2 successive rounds of keystream bytes value is R plus 1. And in that situation, strangely, in the rth round, both the expressions of Jenkins glimpse, that is SRIR expression as well as SRGR expression, both of them become different than 2 by n, and it becomes 3 by n. And in the R plus 1th round, strange thing happens again. 2 by n remains as 2 by n in the SR plus 1 IR plus 1 case, but in JR plus 1 case it changes to 1 by n, that is it decreases, it doesn't remain 2 by n anymore. And one more interesting thing is SRGR is equal to ZR. Directly we can write with a probability of 2 by n. Now the entire detailed proof is given in the paper, and in the interest of time we are not describing it here. We must remember we are ignoring any terms of order of 1 by n square, and that's how this is represented in this way. Okay, let's move on to the next set of results. Now then, the second category of results we have showed, it's a very interesting thing, that Flurer-Magru biases. Now what is Flurer-Magru biases? In 2000, Flurer and Magru, they came out with a result experimentally that in RC4 there are side-by-side bytes in the key stream, right, ZR, ZR plus 1 in certain places and with certain values where those are having higher probability than the random association, right? Random association should be 1 by n square, but they have showed it actually is higher than that, 1 by n square plus 1 by n cube. Now what we are showing here is that in such cases of Flurer-Magru biases, there are certain glimpses of the internal state array that is possible to find out with a higher probability, and this was not found out earlier, that where is the source of Flurer-Magru bias and where is the bias coming from. So that positively or negatively biased internal state array glimpses we are directly finding out. Again, interesting aspect is you can see that it's not dependent on GR in many cases. Now there is also a lag1 digraph. The Flurer-Magru bias is side by side 2 bytes, but lag1 means suppose in I equal to 0 and I equal to 2, these two positions, if we take Z bytes, that is keystream bytes, it has been shown that there are biases of these two interleaving bytes. Similarly, there are such dependencies between the n minus 2 and the 0th byte. So such kind of lag1 digraph results which have been found out earlier in other papers, we are showing in this particular paper, even for those cases there are glimpses of ace array that is possible to be found out. And these are the detailed results, tabular format, we have presented it here, and these are all proved in the paper in detail. And as you can see, the way to look at it is that any particular row, right, it corresponds to Flurer-Magru a particular bias. Say particular bias is 0 0, ZR, ZR plus 1, 0 0, having a higher bias. Now where is the source of ZR? In the rth round we are saying that SR IR plus 1, that particular place is biased by 2 by n. Similarly, in the round R plus 1, SR plus 1 IR as well as SR plus 1 JR, both can be viewed as sources because both are biased. One is biased as 2 by n, the other one is biased as 3 by n. In fact, there are some interesting results in this table. You can see that there is also in the row 12, there is a bias where the probability is actually 0. That means when 0 comma I plus 1 is the side by side two Z values, ZR equal to 0 and ZR plus 1 equal to I plus 1, in such situation, in the R plus 1th round, the probability that SR plus 1, IR plus 1 will be equal to I plus 1 is completely 0. So there is no chance of the source coming from that particular place. So this is like a negative bias that we have found out, right? So as you can see that 3 by n, 2 by n, 0, different types of biases that are there in this particular table. And the next table shows, as we said, for lag 1, that is suppose ZR plus 2, which is 0, 0 at I equal to 0, or ZR plus 2 at I equal to 0 n by 2, 0, or I equal to n minus 2, there the value of ZR equal to 0 and ZR plus 2, which is I equal to 0, ZR value is 0. That kind of places, in all these places also we have found out source of ZR and source of ZR plus 2, and in one place, in fact, you can see the fourth row, there is a bias of 4 by n also that we have found out, which is pretty high. That is, in such situation where lag 1 bias is there, SR plus 2 GR plus 1, that is biased by 4 by n. Now the next set of results is interesting, where we are showing that in Flurer-Magrieux biases, there are also situations where Jenkins correlations gets modified, and this is the place where we are showing the same table, but now we are showing that the SRIR and SRGR, both these values are getting biased, and in some cases you can see that 4 by n bias is also there. Now it was never shown earlier or proved earlier that Jenkins results can get modified to such an extent, but we are showing that there are numerous occasions where this can happen, and not only that, we are also showing that in the lag 1 biases, that there are biases even of the range of 4 by n. And to conclude, we say that we identify here in this paper several new cases where the secret state information of RC4 is revealed with high probability, higher probability than the random association. And with so many additional information related to non-randomness in the state of RC4, it is important to examine whether one can obtain further cryptanalytic results related to RC4. That's the future direction in which we would like to work, and thank you all of you for your patient hearing.
Hi everyone, I'm going to present this paper about mixed-ray integral attacks on reduced round AES with unknown secret hashblocks. The attacks that we are going to present are in the low data scenario. So as first thing, I would like to recall what a low data scenario is. So when we want to evaluate the security of a cipher or of an hash function, we usually try to maximize the number of rounds that we can break without exhausting the full code book or the key space. And this is very, very important because it allows us to determine the security margin, for example, of a cipher. However, in many cases, by exploiting this approach, the attacks becomes non-practical. So they are very close to brute force attacks. Low data scenario is a bit different. So in a low data distinguisher or in a low data attack, the idea is to impose some restriction on the attacker resources. And this is much closer to what happens in real life. In particular, in the low data scenario, the time complexity of the attack is not limited, beside the natural bound of the exhaustive search, while the data complexity is restricted to only a few known or chosen plaintext. So in this paper we focus on AES, and we are going to present a new secret key distinguisher and new key recovery attack for round reduced AES. We think that the most important result of our paper is a new secret key distinguisher for pre-round of AES, which is independent of the secret key. We call this distinguisher an impossible mixture integral distinguisher. Integral because we use a zero-sum property. Mixture because the starting point of this distinguisher is the mixture differential distinguisher proposed at FSC 2019. And impossible because the property that we are going to prove, that we are going to exploit, holds with probability 0 for the case of free round of AES. Here we have a comparison between our distinguisher and other distinguishers in the literature. In particular, I think the most interesting comparison is between our distinguisher and the truncated differential one. As you can see, our distinguisher requires half of the data that the truncated differential distinguisher requires for the same probability of success. For example, if you want to distinguish pre-round of AES from a random permutation with probability of around 65%, our distinguisher requires only 6 chosen plaintexts, while the truncated differential one requires 12 chosen plaintexts. And in a similar way, if we want a probability of success of 95%, our distinguisher requires only 10 chosen plaintexts, while the truncated differential one requires 20 chosen plaintext. There are other distinguishers in the literature. In particular, we have the integral 1, the zero sum, which requires 2 to the 8 chosen plaintext. And finally, we have the yo-yo distinguisher, which actually require a total of 2 chosen plaintext and 2 adaptive chosen ciphertext. But I mean, here the scenario is a bit different because adaptive chosen ciphertexts are required. In these two last cases, the probability of success is very, very high, let's say approximately 100%. So I think this is our main result, and large part of this presentation is about this new distinguisher. But apart from that, we're going to present new key recovery attack for AES, either in the case of a non-S box or in the case of secret S box. So in particular, we are going to present new attacks on 4-round AES 128. Our attacks requires 6 chosen plaintexts, but they don't exploit the details of the key schedule. So among the attacks that they don't exploit the details of the key schedule, our attacks are the best one. If you also consider the key schedule, the details of the key schedule, there are other attacks that are better, and in particular, I think this is the most interesting one because the cost is practical and it requires only 4 chosen plaintexts. But again, this attack requires exploit the details of the key schedule. So if you change the key schedule, this attack must be modified. We also consider the case of 3 rounds of AES with a secret S box. So the idea is to replace the AES S box with a secret one, and we propose a new attack in this scenario, which has the lowest data complexity. So in the case of a secret S box, there are 2 strategies that an attacker can exploit. The first one, this strategy S1, in this case, the attacker first find the details of the S box and then exploit the details of the S box in order to find the key. There is also another strategy where the attacker directly finds the key without finding any details of the S box, and in this case, the idea is to exploit some particular properties of the matrix that define the mixed column operation. So, in our attack, we exploit the first strategy, so we are able to find the key and the details of the S box faster than these 2 attacks that are present in the literature and that exploit the second strategy. So the presentation is organized as following. First of all, I'm going to recall AES, then I'm going to focus on this new mixed integer distinguisher for 3 rounds of AES. I will briefly present these key recovery attacks, and finally I will conclude with some open problems for future work. So what about AES? Well, AES is a SPN block cipher which is based on a design principle known as the white trade design strategy. The block size is of 16 bytes, which are organized in a 4x4 matrix. The key size is of 16, 24, or 32 bytes, and depending on the key size, we have 10, 12, or 14 rounds. Each round is composed of 4 steps. We first have the key addition, then we have the S-box layer, so basically the only nonlinear operation that works at byte level, and then we have 2 linear operations, which are the shift rows and the mixed column operation. For the following, I'm going to record the subspace tree notation that allows us to describe this attack in an easy and formal way. And in order to do this, I'm going to define the following subspaces: the column space, the diagonal space, the inverse diagonal space, and the mixed space. So, the diagonal space is a subspace of text with either active or constant diagonal. So, for example, in this case, we have the first diagonal which is active and the other ones are equal to 0. So, we denote the diagonal space by the letter D, and this index 0 basically refers to the position of the active diagonal. Now, if we take a coset of this diagonal space, it is easy to prove that after 1 round, this coset is mapped into a coset of a column space, which is basically a subspace where we have either active columns or constant column. Now, if we consider another round, and if we start with a coset of a cons subspace, then after the S-box and the shift rows operation, this coset is mapped into a coset of an inverse diagonal subspace, which basically is defined as a subspace of text with either active or constant anti-diagonal. So anti-diagonals are like this. And then if we consider the full round, we have at the end a coset of a mixed space, where the mixed space is obtained by applying the mixed column to this inverse diagonal subspace. So we have that the diagonal subspace, the column subspace, and the mixed subspace form a subspace trail of AS of line 2, in the sense that each coset of a diagonal subspace is mapped into a coset of a column subspace after one round, and that each coset of a column subspace is mapped into a coset of a mixed subspace after another round. This result can also be described using the classical truncated differential notion. So here we consider the difference between two texts, a white byte and not a byte with zero difference, and a black byte and not a byte with non-zero difference. If we have two plain text that differs just in one diagonal, then after two rounds, where the final mixed column operation is omitted, the two corresponding ciphertexts differs in one anti-diagonal. Equivalent, if we take two plain texts that are in the same coset of a diagonal subspace, or if you want, whose difference is in a diagonal subspace, then after two rounds, the corresponding ciphertexts are in the same coset of a mixed subspace with probability 1, while for the case of a random permutation, this happens with probability to the power of minus 96. Okay, using this notion, we are going to recall first the mixed differential distinguisher that was proposed at FSCTOS 2019, and then using this distinguisher starting point, we are going to propose our new distinguisher for 3 rounds of AES. In order to do this, we introduce this notation. Without loss of generality, we just focus on coset of column subspace where the first column is active, and we take text in this affine subspace. So given a text P in this coset, we have that P can be written as A, which is the constant that defines the coset, plus this matrix, where obviously the second, the third, and the last column are equal to 0. So for simplicity, we can just rewrite this text in this way, so we can just refer to such text via its generating variables. Okay, so consider two plain texts, P1 and P2, in a coset of column space, where these are the generating variables of the first plain text, and these are the generating variables of the second plain text, and we assume for simplicity that all generating variables are different. Then it is possible to prove that if you consider the corresponding ciphertext after 4 rounds, and if you take their difference, this difference belongs in a mixed subspace if and only if there are other pairs of plain text for which the corresponding ciphertexts have the same property. And these new pair of plain texts are generated by mixing the generating variable of P1 and P2. For example, in this case, we swap the first generating variable, in the second case, we swap the second generating variable, and so on, for a total of 8 possible combinations. Now, we have a similar result if some of the generating variable of the first plain text are equal to the generating variable of the second plain text. For example, in this case, we have that W is equal for P1 and P2. So we have the same result where here we are just going to mix the variables that are different, and we replace W by omega, where omega can take any possible value in F2 to the 8. And the same happens if two variables are equal for P1 and P2. Now, I'm not going to record the full proof of this result, which you can find in the corresponding paper. I'm just going to record the idea of the proof, because this is the starting point for our new distinguisher. So we have a distinguisher, we have a property on 4 rounds of AES, where basically we start with a coset of a common space, and we finish with a coset of a mixed space. And we consider the property that two texts are in the same coset of this mixed space M. But as we have seen before, two texts are in the same coset of a mixed space M if and only if 2 rounds before they are in the same coset of a diagonal space D. So instead of working with 4 rounds and with the mixed space M, we can just focus on the first 2 initial rounds and replace this mixed space with a diagonal space. And the idea of the proof is the following. Given P1, P2 as before, and at P1 and at P2 as before, so where the idea is that at P1 and at P2 are obtained by mixing the generating variable of P1 and P2, the proof follows from this fact, so that the difference of P1 and P2 after 2 rounds is equal to the difference of at P1 and at P2 after 2 rounds. In other words, if we take the sum of these 4 texts, this sum is equal to 0. So we have a zero-sum distinguisher for 2 rounds of AES. This is not very interesting because the truncated differential distinguisher on 2 rounds of AES is much more efficient, but this is the starting point for our new distinguisher on 3 rounds of AES, which is the following. Let's consider 4 plaintext P1, P2, P3, and P4 in the same coset of common space 0. These are chosen plaintext and they are defined in the following way. So P1 is defined as x1, y1, z, and w. P2 is defined as x2, y2, z, and w, where z and w are equal, and where x1 is different from x2 and y1 is different from y2. And then we take P3 and P4, where basically the first 2 variables are equal, here and here, but then we have z prime and w prime that are different from z and w. So these are our 4 chosen plaintexts, and the property is the following. So let's consider these 4 plaintexts, and let's consider the corresponding ciphertext after 3 rounds. So suppose that 2 ciphertexts are equal in a particular byte. So this subindex I and j denote the position of the byte. So if these 2 ciphertexts are equal, then for 3 rounds of AES, it is not possible that the other 2 ciphertexts are different. And this is independently of the secret key, of the details of the S-box, and of the mixed code matrix. So in other words, if we have 2 ciphertexts that are equal in 1 byte, then also the other pair of ciphertexts must be equal in such byte. Or if you want, if 2 ciphertexts are different in a particular byte, then also the other 2 ciphertexts must be different in that particular byte. This event, so the fact that 2 bytes are equal, 2 ciphertexts are equal in a particular byte and the other 2 are different in the same byte, can happen for a random permutation, and this allows us to distinguish 3 rounds of AES from a random permutation. So first of all, we are going to prove this result, which I think is the most important result of our paper, and then we try to understand the data cost of this distinguisher. So how to prove this result? Well, if we have 4 plaintexts defined in this way, we have that the corresponding sum after 2 rounds is equal to 0. So potentially, if we consider 3 rounds of AES, we can just set up a key array attack. So we have the plaintext defined as before. After 2 rounds, we have this zero-sum distinguisher, which is independent of the secret key. And then if we have the corresponding ciphertext after 3 rounds, we can just work at byte level, guess the key, partially decrypt, and find the key. So we know that for 3 rounds of AES, there must exist a key for which here we have the zero sum, so a key that satisfies this equality. This key must exist, and this key is equal to the secret key. This is quite trivial. So what is the idea? Well, if the ciphertexts are generated by a random permutation, then it's possible that such key does not exist. So it's possible that there is no key for which this equality is satisfied. Remember, for AES, this key exists, it's a secret key. For the case of a random permutation, it is possible that such key does not exist. Now, we can obviously set up the key recovery attack. This is already a distinguisher, but the question is, can we check this fact without finding the key? So it is possible to find an equivalent property on the ciphertext, which is independent of the key, that if satisfied, implies that no key that satisfies this zero equality exists. And the answer is yes, and it's exactly the property that we showed you before. So assume that we have two ciphertexts that are equal in one particular byte, and such that the other two ciphertexts are different. Now, if we have the equality as before, and if these two ciphertexts are equal, then obviously this sum is equal to 0. So this equivalent reduces to this one. But now it's very easy to check that this equivalence has one solution, at least one solution, if and only if these two ciphertexts are equal. Otherwise, there is no solution. But this is a contradiction. So if we have this situation, then there is no key that satisfies this equality. So if we have this situation, for sure, the ciphertexts have been generated by a random permutation. We don't have to find the key. We already know that if this happens, for sure the ciphertexts are generated by a random permutation. So in the case of a yes, we need that either these two ciphertexts are equal and these two ciphertexts are equal, or that these two ciphertexts are different and these two ciphertexts are different, working at byte level. Okay, so we have this distinguisher, so we want to understand the data cost of this distinguisher. So let's consider P1, P2, P3, P4 as P4. And let's consider the probability. So let's consider the case in which the ciphertexts are generated by a random permutation. Let's consider the probability that this event happens. So the probability that two ciphertexts are equal in a particular byte and that the other two ciphertexts are different. It's not hard to check that this event happens with probability approximately 30%, and this is due to the following fact. So we have that the probability is equal to 1 minus the probability that this event doesn't happen. So here we have 16 because we have 16 different bytes. And so this refers to the case in which all bytes of these ciphertexts are different. And this refers to the case in which all bytes are equal, or this event is satisfied. So these two bytes are equal, these two bytes are equal, and so these two bytes are different from these 2 bytes. Okay, so let's consider n set of 2 pair of plaintext, P and P prime, where P and P prime share the same generating variable Z and W, and where X is different from X prime and Y is different from Y prime. So we have n different set where where we basically take different values of Z and W. So given this n set, we can construct n prime different set S, where n prime is approximately n squared alpha, of 4 pairs PP prime and then at P prime. So each one of these sets does not satisfy the required property with probability approximately 30%. So if we want to distinguish a free round of a yes from a random permutation with probability that is higher of this probability probe, we need that the number n prime of different set S satisfy this inequality. For example, if we want to have a probability of success of 95%, then we need at least 10 chosen plaintext. Now, actually this set, so the set defined in this way, so by combining all these pair of plaintexts, are not independent. So this actually means that the probability, so the real probability is actually smaller than this one. So this is only an approximation. So in the paper we explain this fact in more details, here I just want to show that the real probability is actually smaller than the theoretical one, but the gap is not too big. For example, this is the number of chosen plaintext, this is the theoretical probability that we obtain using this formula, and this is the practical probability. And you can see, for example, that when we use 10 chosen plaintext, we expect a theoretical probability around 97.6%, while in practice we have a probability of success of around 95%. So the gap is reasonably small. Okay, so we have a new secret key distinguisher for 3 rounds of AES. As I said, we also propose a new key recovery attacks, but these attacks are quite standard, so I'm not going to spend too much time on this. In particular, if we have P1, P2, P3, P4 as before, we have just seen that the sum of these 4 texts is equal to 0 after 2 rounds of AES. So it's very easy to set up an attack on 3 rounds of AES, working as in the classical integral attack. So we have the plaintext, the corresponding ciphertext, we work at byte level, so we guess the key at byte level, we partially decrypt, and we find the key that satisfies the 0 sum. In a similar way, we can also set up this attack on 4 rounds. So again, we have the plaintext as before, we have the ciphertext after 4 rounds. In this case, we have to partially guess an anti-diagonal of the final round, partially decrypt, and then working at byte level, we again guess the key and we check that the 0 sum is satisfied or not. If it is not satisfied, the guessing key is obviously wrong. So this is very, very similar to the classical integral attack on AES. So I'm not going to give more details. We also consider the possibility to set up an attack on 4 rounds of AES based on the 3 round impossible mixture integral attack integral distinguisher. This is obviously possible, but we found that this is not competitive with respect to other attacks in the literature. So I'm not going to give details about this. And finally, as I said, we also consider the case of AES with a single secret S box. So the idea is to replace the AES S box with a secret S box, and this basically allows to increase the size of the secret information. So, for example, for the classical AES, we have a secret key of 128 and 256 bit. In the case of a secret S box, we have this amount of secret information. So the question in this case is, how does the security of AES change when the S box is replaced by a secret S box about which the adversary has no knowledge? So it is possible to find the key and even the S box by setting up an attack whose cost is smaller than 2 to the power of 128 for AES 128, for example. And the answer is yes. So there are many attacks in the literature. So in particular, as I said at the beginning, there are 2 strategies. Here we focus on the first one, where the idea is to first find the S box up to some unknown additive constant A and B, and then to use this knowledge in order to find the key. In particular, we exploit the same strategy that has been proposed in this paper by DISE and et al. At FSC 2015. In such case, the authors first find the S box using a particular technique that is described in that paper, basically a technique that is based on the zero-sum property, and then they exploit an integral attack in order to find 15 bytes of the secret key for 4, 5, and 6 rounds of AES 128. In our paper, we basically use the same strategy in order to find the S box, and then we are going to use our zero-sum property in order to find the key for 3 rounds of AES, where our zero-sum property requires only 4 chosen plaintext, while in the case of a classical integer attack, the attack requires 256 chosen plaintext. That's all from my side. So again, as our main result, we presented a new secret key distinguisher on free round of AES, which is independent of the secret key and which has the lowest data complexity in the literature. But there are obviously open problems for future work. So first of all, if it is possible to set up an impossible mixed integrity distinguisher on 4 rounds of AES, well, the idea would be to use the classical integrity distinguisher on 3 rounds as starting point. And finally, if it is possible to exploit this distinguisher that we propose in this paper in order to present new key recovery attack for round-reduced AES in the low data scenario, both in the case of known, in the case of the known or in the secret S-box setting. That's all. Thanks for your attention.
I'm Abhishek Kumar and Sumitra Kumarsanadja, and I, Aaron Lamboy, will present. This work is inspired by the works of Nyberg and Knudsen, as well as the design strategy of the AES, also named the White Rail design strategy. Many designers use this design strategy to prove security bounds on the ciphers. In this work, we want to show that these bounds are not always accurate and things can go wrong in a very delicate manner. We show how a provable secure block cipher can still be distinguished from a random permutation. Thus, as the title says, counting active S-boxes is not enough. So, as this presentation is about symmetric cryptography, I will give a very quick refresher of block ciphers. So, basically what you see here is a block cipher. There's a function E that takes as inputs a P and a K and outputs ciphertext C. Now, why is it called symmetric? Because the inverse of the function, D for decrypt, takes the same key and the ciphertext and produces the plaintext P. Now, what we will look at in this paper, or in this presentation paper, are distinguishers and how to bound the best possible distinguishers for a cipher. A distinguisher is basically an algorithm such that we distinguish the cipher from a random permutation. So the distinguisher that we will be looking at is the differential distinguisher introduced by Biam and Shamir in 1993, which basically looks at relationships between the input and the output difference. So the input difference would be a plaintext P XORed with some plaintext P prime, and then we follow the difference through the cipher, which we call a characteristic, and we'll get output difference C and C prime. And if the probability for such a characteristic is high enough, then we can use this to distinguish the cipher from a random permutation. Now, as I said in the introduction, we are looking at the White Rail design strategy, and this is basically based on the work of Nyberg and Knudsen from 1995, which provided us with a framework to prove that the cipher is secure against differential cryptanalysis. So basically what they did, if we have a differential in a cipher which happens with a probability P, then we need at least 1 over P data, so inputs, input pairs with a certain input difference to be able to distinguish this, to see this property in the cipher. Now, if we have a cipher, a symmetric cipher, we also have a block size, and if we take that to be n, then we can only have at most 2 to the n input pairs with a certain input difference. Now, we can thus conclude that if the best differential, the probability for the best differential is smaller than 2 to the minus n, the cipher is secure against differential cryptanalysis. Now, so the work by Nyberg and Knudsen was the basis for the white trail design strategy that was also employed in the design of the AES. And what it does, it looks at what the white trail design strategy does is looking at the construction of the cipher, and it tries to bound the probability of the best differential characteristic. To do this, we split the cipher into linear and non-linear parts, and as usual, we will take the non-linear components to be S boxes. So from now on, I will say S box and non-linear components a bit interchangeably. We then compute. We can compute the maximum differential probability through an active S box. And then if we count the minimum number of active S boxes in a characteristic, in any characteristic of R rounds, then we can compute a lower bound for any characteristic of R bound. So a lower bound on the probability, of course. And this we can, of course, also use to compute the minimum number of rounds that we need for the security level that we want. As a side note, as most of you probably know, this is used by a lot of designers to, as a very convenient tool to approximate the strength of the cipher against certain attacks, such as differential and also linear cryptanalysis. There are some assumptions being made, and those assumptions, as we will see later, can have actually a bad effect on the security. So you won't get the security that you hoped for. And to show this, I will introduce two ciphers that are very related to each other, and they will show the problems that you get when only relying on the white trail design strategy in the analysis of a new cipher. So, as I said before, we will be looking at two ciphers, but they're very related. So both of the ciphers will have a 128-bit block and use the AES S box for the nonlinear layer, which is called here the S layer. We'll have a permutation layer P, which basically is an MDS matrix, an 8x8 MDS matrix. So what we will have here is we have a 128-bit input that we split into two. So it's a Feistel construction here. And we have some 64-bit round key that we don't really care about, just take some uniform random value for that. And then we compute the S box, like 8 S boxes in parallel, and we combine those with a MDS matrix P. This cipher has 16 rounds, and as we will show in the next slides, if we follow the white trail design strategy, this is plenty enough to be secure against differential cryptanalysis. It is secure enough against differential cryptanalysis. And we computed the minimum number of active S boxes for this cipher using MLP for R rounds and R between 1 and 16, of course. So if you look at this table that depicts the number of active S boxes for the number of rounds, we see that at round 11, we have 22 active S boxes. And if we recall that the AES S box has a maximum differential probability of 2 to the -6, we can compute that then the the best probability of a characteristic is 2 to the -132. If we look at 16 rounds, so that's already at 11 rounds, it's plenty good enough if you look at characteristics. And if we go to 16 rounds, then we see that 39 that we at least have 39 active X boxes for the best characteristic, and this will give us a probability of 2 to the minus 234, which of course is more than enough for 128-bit block size. Now we'll move to the second cipher, and we can see here that what we basically did was squish 4 rounds or 4 of these SP layers into 1 round. And we did that to reduce the number of rounds. And to keep the resources the same as the previous cipher, and as we will see, the security is also quite similar to the previous cipher. We only have 4 rounds in this construction, but we will have the same number of SP layers. So as we will see, the security won't be much worse. Like there are 3 active S boxes less, but that doesn't really matter too much. Now, to compute the number of active S boxes, we take a slightly different approach than for the first cipher, because it's easier here to do, because we know that P is an MDS matrix, and we also know that if we have 2 consecutive SP layers, we need to have at least 9 active S boxes if the input to the SP layers is of course active. And since we have 4 consecutive SP layers, we will need at least 18 active S boxes in 1 round, in 1 active round. And that means that the input to the round is non-zero. Now, we know that for a Feistel network of 4 rounds, we have at least 2 active rounds in differential cryptanalysis. So that will give us, for the 4 rounds, at least 36 active S boxes. And this gives us a lower bound on the probability of the best differential characteristic of 2 to the minus 216. So again, this is plenty. But we'll show that actually this analysis is not that accurate if we analyze it a bit more carefully. Okay, so let's have a look at a differential distinguisher on a 4-round Feistel network, and we see here that we have 2, as I said before, we have 2 rounds that are active, round 2 and 3, and if we have a 0 alpha input difference, we get a beta 0 output difference with probability P1 times P2, assuming that everything is independent of each other, of course, otherwise the probability will change. But we, as always, assume here that we have round independence. Now, what I want to do here is to look at the round functions as sort of black boxes for now, where F1 gets us the input, the round keys, and the input. So it's basically, it's a 64-bit permutation given a set of round keys. So that if we can compute a DDT for F1, F2, F3, F4, and of course only for F2 and F3, this is useful, but the DDT for F2 and F3 are different, but we can say something about it. And if there is a large enough entry in the DDT of F2, which we'll call DDT2, and a large enough entry in F3 that we call DDT3, then we can have a distinguisher. So what we need actually is in DDT2 a transition from alpha to beta with a high value, and in DDT3 a transition from beta to alpha with a high value. And if that happens, we have a differential distinguisher for the cipher, and thus also the cipher that we discussed before with the 4 rounds. Now, if we want to say something about the DDT, then
we should look at how the distribution of the entries of the DDT behave. And luckily for us, O'Connor did that in '93 and came with this distribution. And now what is left to do is to compute if we can have this event that DDT2 alpha goes to beta with a high value, and beta goes to alpha with a high value in DDT3. And if we follow this distribution, then in each of the 64 rows, we have 8 entries of 32. Thus, with a high probability, we'll get DDT2 alpha goes to beta with a value of 32, and also with a high, and DDT3 beta goes to alpha with a value of 32. Now, if we fill in these figures into the differential that we got before, we'll see that P1 turns into 32 times 2 to the minus 64, and P2 as well. So the probability of this differential now becomes 32 times 2 to the minus 64 squared, which gives us 2 to the minus 180, which is a lot lower than what we predicted with the white trail analysis before. So does this distinguish the cipher? For that, we need to first look at one other thing, because we need to distinguish it from a random permutation on 128 bits. And we know that this permutation, we can also create a DDT for that, or we can see the differential probability of going from input difference to a output difference in the DDT. And following O'Connor's work, again, we know that with high probability, the maximum value in this DDT for a random permutation will be 100. And this will give us a probability of approximately 2 to the minus 121 for any differential in the cipher. So we can conclude that this distinguisher is this cipher is distinguishable from a random permutation. So now the most important part: what went wrong here? Because clearly we are contradicting the proof that we gave with the white trail analysis that we did earlier. Now that's not entirely true, of course, but we'll come back to that later. So what we have is a differential distinguisher with the probability of 2 to the minus 118, while the wild trail analysis gave us a probability for the best characteristic of 2 to the minus 216. And the problem here is the difference between the differentials and the characteristics, because the differential you can see as a set of differential characteristics that all go from one input difference to the same output difference, like to a output difference. And what the white trail design strategy does not account for is the existence of differentials. And this actually is one of the major pitfalls of using the white trail design strategy for the analysis of the cipher. So to conclude, I will repeat the title. Only counting active S boxes is not enough. Does this mean that we should not use the white trail design strategy? No, it is a very useful and powerful tool for analyzing ciphers, but we should not forget that it does not prove a cipher to be secure against differential or linear cryptanalysis. And we should always be aware of the implicit assumptions, namely the round independence assumption, and that we are looking at characteristics instead of differentials. Because if we do not take those in mind, bad things can happen, as we have seen in this presentation. And as a last note, I would also like to stress that this is, of course, not implying that this, of course, does not only apply to differential cryptanalysis, but also linear cryptanalysis. Thank you for listening, and I hope you enjoyed the talk.
The segment Signatures MAC covers the following talks: the multi-base discrete logarithm problem by Mihir Bellare and Weidai, skipping the queue in group signatures by Oliver Blasey and Sakib K. Kakwi, incremental cryptography revisited, PRFs, nonces, and modular design by Vivek Arte, Mihir Bellare, and Louisa Khate.
Hello, my name is Weidai, and my talk today is on the multi-base discrete logarithm problem, type reductions, and non-running proofs for Schnorr identification and signatures. Then this is joint work with my advisor, Mihir Bellare. The Schnorr signature scheme is one of the earliest known number theoretic signature scheme, and it was first proposed by Schnorr back in 1991. However, somewhat unfortunately, due to past patent status, it did not see practical adoptions until recent work of EDDSA, which is based on Schnorr, by Bernstein et al. Back in 2011. Now it is in the standardization process, and it's also widely deployed among numerous applications, protocols, and platforms. Compared to DSA, the Schnorr signature scheme enjoys a rich body of research, not only supporting its security, but also extending into other applications. It was first proved secure in both generic and standard model around the turn of the century. Later, the landscape is further modularized and are extended to many fancier signature schemes, such as multi-signatures, ring signatures, and threshold signatures. However, there has always been a gap between standard model security guarantee and expectation of security in practice. In this work, we identify and close the gap via a discrete log-like problem, which we name multi-base discrete log. Let's start by recalling the Schnorr signature scheme and the underlying identification protocol. First, let's fix a group of prime order P with generator G. The secret key small x is sampled uniformly at random from ZP, and the public key big X is G raised to the small x. The signature scheme can be seen as the Fiat-Shamir transform applied to the underlying identification scheme. So, what is the Schnorr identification scheme? Well, Schnorr identification scheme is a 3-round protocol between the prover and the verifier. And the prover will take in input the public key X, which is also given to the verifier, but also, in addition, the prover has access to the secret key small x. In the first round, the prover will sample random R from ZP and computes G to the R, which is then sent to the verifier as commitment. Upon receiving the commitment R, the verifier will choose a random challenge in C from uniform random from ZP and return it to the prover. The prover, upon receiving the challenge C, will compute a response Z as follows. And the response Z is computed exactly to make the verification equation hold. And the verification equation is G to the Z is equal to R times big X to the C. And upon receiving the response, the verifier will check indeed that the verification equation will hold. To turn this into a signature scheme, the Fiat-Shamir transform eliminates the interaction by hashing the random commitment R and message to be signed to derive the challenge C. In particular, in the signing algorithm, we'll first compute the random commitment. Then we'll derive the challenge C using the random oracle, a hash function model as random oracle, applied to the commitment R and message to be sent M. And the response is derived as before Lastly, the signature is set to the random commitment and the response Z. Verifying a signature on a message M amounts to first deriving the challenge C using the hash function, and then checking that the verification equation indeed holds. The benefit of viewing the signature scheme in this modular form is that the UFCMA security of the signature scheme reduces to the INDCPA security of the ID scheme. INDCPA means impersonation under passive attack, and we'll recall it in a bit. UFCMA is the standard security goal for signatures and forgeability under chosen messages attack. This result was first shown by Abdallah N. Balari and Namprampri. The lemma says that given an adversary attacking the UFCMA security of Schnorr signature, then an INDCPA adversary can be constructed to break the INDCPA security of the underlying identification scheme. And if Q is the number of random oracle queries of the UFCMA adversary, then there's a multiplicative loss of Q and additive loss of Q squared over P. This means that the core question here is the security of Schnorr ID scheme, and we can focus on it. Security against impersonation and a passive attack requires that a prover cannot impersonate if it only gives passive access to transcripts. In particular, it is modeled as a game, and in this game, the adversary will submit a commitment R, get back a challenge C, and to win the game, the adversary needs to provide with the correct response Z. And in addition, the adversary can at any point obtain valid transcripts via the oracle TR. When considering INDCPA security of Schnorr ID scheme, we can largely actually ignore the presence of the TR oracle because of the honest verifier zero knowledge property of the protocol. The INDCPA security of Schnorr ID scheme is typically proved based on assumed hardness of the R problem in the underlying group. The reduction uses rewinding, running the INDCPA adversary twice in this with the same commitment R to extract the discrete logarithm of the public key X. Since we essentially need 2 runs of the INDCPA adversary to succeed, there is a square root loss in the advantage, as shown in the formula here. And we know that there's no known tight reduction from discrete log, and it's likely that none exist, as evidenced by Kiltz, Masny, and Pan. Now, of course, one can always assume that the INDCPA's security of Schnorr directly in the group, but we ask, can we prove security from some DL type assumption that's independent of Schnorr identification? And before we answer this question, let us see why eliminating the square root gap in concrete security, it's important. Again, let G be a group of prime order P with generator G. Recall that the best known attack for discrete log on elliptic curves is basically for example using polar row, which achieves success probability of around t squared over p in time t. And in practice, is basically always assume that Schnorr identification scheme using group G will have the same security as discrete log. But with the current proofs, as shown before, this is not justified. In particular, there's the square roots. And so, for example, when P is a 256-bit prime, we compute, for 3 example values of running time, the corresponding upper bound on success advantage of any discrete log or INDCPA adversary. And you can see that indeed the square root loss here does affect quantitative results. So this gap between theory and practice is unsatisfactory, and we'd like to do better via our new assumption. And the idea that to use different assumptions to justify security, it's really not new. And consider, for example, the Diffie-Hellman key exchange protocol. We do not know how to prove it from a discrete log, and so therefore we prove it from computational decisional Diffie-Hellman assumptions. And such scenario has essentially has happened in a lot, essentially in especially in parent-based cryptography. In that landscape, many bilinear group assumptions has been proposed to prove security of more advanced schemes such as IBEs and homomorphic signatures. Now, of course, these knobs cannot be turned without justification. The hardness of these problems must be justified in idealized models, such as generic group models or algebraic group model. And they need to be verified by cryptanalysis. And for these problems, the hardness is usually seen as becoming more well-founded as the problem ages. Whereas previous bodies of work turn these knobs to achieve feasibility of security, we ask, can we turn the knobs to tighten the reduction loss? And our answer to this is multi-base discrete log problem, or MBDL for short. Again, like GB, a group of promoter P and with generator G, let's first recall the game for DL, which simply samples a random target point Y and asks the adversary to produce the discrete log of the target point Y base G. The MBDL game adds the following on top of the standard DL game. First, additional to the target point Y, the adversary also get a list of random group elements x1 to xn. And they are sampled so that they are not identity elements. Second, the adversary is allowed to query a discrete log oracle, but only exactly once, specifying an index I and the group element W. The oracle shall return the discrete log of W base xi, where this I was chosen by in the input of the discrete log oracle. In effect, the adversary is allowed to take one discrete log, base any xi of his choosing. Lastly, again, to win the game, the adversary needs to find small y, which is the discrete log of target point big Y base G. Crucially, we note that the one query restriction on the discrete log oracle it's crucial. If not, if the adversary can obtain two queries of this oracle, then it can find the discrete log of Y base G trivially just by simply relating two calls of the discrete log oracle. Say first on the base G and then on the target point Y, but base x1. And the intuition on why such a problem could be hard is that essentially the discrete log oracle takes a discrete log, but with an unrelated point, which shouldn't really help to solve discrete log base G. And as suggested earlier, the only way we really know how to justify hardness of a problem is using idealized models. And we show here that MBDL is indeed hard in the generic group model. In particular, it holds with the same quantitative bound compared to discrete log. Okay, we now show how to prove INDCPA security of Schnorr ID scheme from MBDL tightly. Recall that the INDCPA game of Schnorr ID requires the adversary to produce a valid response Z for some randomly chosen challenge C and previously committed value R. Our theorem says that the INDCPA advantage of any adversary A is highly bounded by the MBDL advantage of a related adversary B that can be constructed from A. And note that this relation is tight here and there's no square root loss. And the construction of B goes as follows. So first, let us note that if R, C, and Z is a successful transcript, then the response Z must be the discrete log of this group element, which is R times X to the C. So this means that impersonator can take the discrete log of exactly this group element. So our goal will actually to be set this group element to our target point y. And the reduction proceeds as follows. First, our adversary B will receive the base X and target point Y from the MBDL game. So here we're going to restrict to just n equals to 1 in MBDL. And the adversary will forward the base X as the public key for impersonator A. And upon receiving the commitment R, the adversary B will instead forward R inverse Y to the discrete log oracle. And so the discrete log oracle will compute the discrete log base X of this group element at R inverse times Y. And this is then forwarded all the way back to the impersonator. And the impersonator will respond with Z, and the adversary B will then use the Z as the guess for the small y. So let's see why the setting the value of R inverse Y as input into the discrete log oracle will work. Well, if C is a discrete log base x1 of R inverse Y, then it means that R times x to the C is Y. So they just simply by plugging this in. And this, recall from earlier, if adversary is basically taking the discrete log of this value, then if it succeeds, then we have found the discrete log of big Y. So we have exploited using the discrete log base X to program Y into this element to be equal to that element. So to sum up, we have constructed an adversary B that succeeds in finding discrete log of a target point Y base G, taking exactly one discrete log base another unrelated base X, and therefore breaking MBDL. So we have shown that the INDCPA security of Schnorr identification relates tightly to the MBDL in the underlying group. As mentioned previously, a positive result for Schnorr identification scheme directly translate to Schnorr signature because of the modular proof of security shown by AABN. Quantitatively, previous result says that when using a composition result by AABN, the NPPA and the so using the results of composition result and the NPPA to DL reduction, we get a bond of this form, and there's a square root around the discrete log advantage. But actually, if one were to do a direct proof using forking lemma, as done originally in Poncho von Stern, the Q here will actually go underneath the square root. Therefore, the eventual bound is a bit tighter. And our result says that actually no square root is necessary here. But we instead will rely on the hardness of MBDL instead of just discrete log. And we conjecture that for adversaries A and B with similar computational resources, MBDL and DL should be equally hard. And this has been verified if A and B are both generic algorithms, as we have demonstrated before. As comparison, we demonstrate that our result is indeed better if one were to instantiate parameters assuming only hardness of DL and MBDL. So here we're going to specify running time, running time and success advantage epsilon. And for for both DL and MBDL, we'll apply the GGM bound relating the group size P to the running time and the bound desired epsilon. And here we'll set T and epsilon to target a 128-bit security level, which means that we're setting T divided by epsilon to be 2 to the 128. And so here we can see that the group size required P2 is strictly smaller than the group size required P1. So P2 is the group size required from our results, and P1 is the one dictated by previous results. And this also shows the results as in the speed up, which is also which is cubic in the bit size improvement. And similar results can be derived for Schnorr signatures, but in addition, we'll have to specify the allowed random oracle queries. We now discuss briefly how we justify the hardness of MBDL in the generic group model. Formally, in the generic group model, fix a set of strings G, and the game shall sample a random injective encoding function, mapping each element from ZP to some string in G. The game keeps track of a list of encodings GL, representing the set of elements that's known to the adversary. And the grouper operation is done via an oracle that takes two encodings of elements, provided that they are in the set GL, and the multiplication oracle will decode them, do the corresponding operation, and then encode them again to return this new encoding, as well as adding it to the list GL. The MBDL game stays the same, with the addition that in the generic group model, we add these this oracle that does group operations. And we provide a theorem that says that if A is a generic group algorithm making Q OP queries, then the advantage of it breaking MBDL is at most this quantity, which is roughly Q squared over P. So here we give the rough proof outline for this. So first, we're going to fix some generic adversary making Q OP queries. And we're going to define an extended transcript to be of the form Z, which is the discrete log oracle response, Y, which is a target discrete log point, and the exponent x1 to xn. Note that this transcript fixes the behavior of the game if you also fix the randomness of the adversary, but it gives more information than what the adversary gets back. So the intuition is that the discrete log oracle query creates a one-dimensional constraint on these variables from ZP. And consider a real run of MBDL. First, we'll sample this small exponents x1 to xn, restrict to that they're now 1, and then we'll sample the targets y, and we'll compute the discrete log honestly, given some index I and group element w. And we'd like to argue that z and y here are independent. But as written here, they're obviously not independent, and they could have a correlation because at w here could correspond to the element generated, by computing multiplication, for instance, of x's and y's. So let's move to a simulator run, in which we can argue this more easily. So instead of sampling all these at the beginning, we won't sample them at the beginning, and during the first and only DLO query, we'll parse the representation of this element w into a product of xi's, so xi to the wi, and the product n times some power of g and some power of big Y. And it turns out that the response here can be sampled without needing to fix other values of x's and y. And in particular, there's kind of two cases. One is the trivial case, and one is the case when we can sample uniform and random. The trivial case means that kind of the response is determined already. And an easy case to think of is if this w is just xi to the wi and with nothing else, then we must return wi. So implemented into this intuition, actually there's more to check, and we'll have to fix all the other elements to kind of sample whether we're in the generic case or not. And if it is, we'll set z to wi, and then we'll sample this xi uniformly at random. And if not, then we sample z uniformly at random, subjected to it not being this value wi, and then solve for xi. And we provide a lemma that proves that these two ways of sampling the transcript provides identically distributed distributions on these transcripts. And with this lemma, the proof will proceed as other GGM proofs, modifying E to be lazily sampled via game hops while incurring a loss or overall loss of the form Q squared over P. one thing to note is that KMP has previously claimed a tight reduction of Schnorr identification from discrete log. Their notion of tightness is ratio-based. In particular, they define a reduction to be tight if it preserves the ratio between the running time and success advantage. Our view is that this definition of tightness does not actually translate into tight security guarantees in practice. Indeed, like both attacks and bounds for DL type problems indicate a quadratic trade-off between success advantage and running time. So our view is that tight reduction for group-based schemes should preserve both running time advantage independently. And we show that this does translate to tight security guarantees in practice. And finally, we believe that MBDL as a DL-like assumption can be applied in other settings. In particular, MBDL can eliminate the need for rewinding in forking lemma-based proofs. For example, Drivers et al. Has shown that multi-signatures, forking lemma usage in multi-signature can be error-prone, leading to insecure schemes. And in the follow-up work, we show that MBDL can be used to prove security of other schemes, such as the Bellary-Nevin multi-signature schemes, MUSIC, 1 out of n signatures, threshold signatures, and as well as new 2-round multi-signatures based on an extended version of MBDL. And that is the end of my talk. Thank you for tuning in.
Hello, I'm Saki Beikakwi, and I'm presenting my work with Olivier Blasi called Skipping the Queue in Group Signatures for Indocrypt 2020. Alright, so let's get started. Let's talk about group signatures. So group signatures are a conceptually simple primitive. It's quite easy to explain them on a high level. However, technically they're quite tricky. And this is for various number of reasons, because of the security requirements that we have, because of the way that they function, because of a lot of interesting things that crop up. But I won't talk about too many of those things. I don't have enough time here, but we'll talk about one of the things here. I mean, we do know how to build group signatures. There are several schemes to build group signatures, but there is one glaring issue with the majority of these signatures. And that is that almost all these constructions rely on Q-type assumptions. Now, in terms of cryptography and provable security, we really want to avoid Q-type assumptions. These are kind of the enemy as far as we're concerned, and where possible, we'd like to avoid them. And so we do. We take a fairly generic approach to remove the reliance on these. And I'm going to talk to you a little bit more about that right now. But first, let's talk about group signatures in detail. So, conceptually, very simple. They allow any member of a group to anonymously sign on behalf of a group. So these signatures are verified under a global group public key GPK, and of course, any member can produce a signature, and this will be anonymous, and all you know is that a member of the group produced a signature. However, these signatures can be de-anonymized by an authority in the case of misuse. So if any member of the group produces a signature that they weren't supposed to, or produces a signature and that leads to some problem, then that can be de-anonymized and that can be traced. So to this end, we actually have two group authorities, the issuer and the opener. So the issuer uses their secret key SKISS to enroll new users. And we can add arbitrarily many users, but not remove them. And that's just the way that our model works. And this is one of the most common models for group signatures. And then the opener can open a signature using their secret key SKOpen. And this is exactly the de-anonymizing factor I was talking about a minute ago. So what the opener actually does is they extract the identity of the party from the signature. So this identity is revealed. What I'm not going to talk about, but I'll just mention on the side, is that normally that this comes with some sort of proof that this was indeed done correctly, and that this can be publicly verified that indeed this person did produce the signature. But okay, so for the remaining work, we're going to focus on the issuing of keys, because this is sort of the point that we've noticed where the Q assumptions pop up a lot, and we looked at why that is and how we can fix that. So, adding new users to the group. How do we actually do this? Well, we consider a scheme in the Belarusi-Zang or the BSZ security model, which is the most common used group signature security model, right? And this is also sometimes called the growing membership group signatures model. The reason for that is, as I said before, is that you can add members arbitrarily, but there is no mechanism to remove them. So even if a signature is open and the user is found to have done something incorrect, you can't remove them. But that's one unfortunate drawback of the security model. In this model, how it differentiates from some other models is that issuing a key is actually an interactive protocol, and in fact, these issuings can be run in parallel, so multiple people can sign up to join the group at the same time. And this requirement is sort of what introduces a lot of the problems. And so the common solution is to use what's called a certified signing key, which is a signing key for a certified signature. And what exactly is that? You might be asking yourself. Well, certified signatures are augmented digital signature schemes. Now, what they are is essentially they're an attempt to model a public key infrastructure, or PKI. So this is this is what they were created for, but they found a lot of use in other things, and in particular here they have a very nice application. So when you're a user in a certified signature scheme system, in addition to getting your verification key, of course your signing key, but mostly the point is the verification keys, you get a certificate cert. And what the certificate certifies, so to speak, is that this verification key is actually correctly formed and well formed, and is indeed a key that has been issued and belongs in the system. So actually, when you verify signatures, you not only verify the signature using the verification key, but you also verify the verification key itself using the certificate. Okay, to do this, we have one authority who's an issuing authority who creates new certificates. Obviously, they have some secret information of their own and they use that to create certificates. And normally this is done as an interactive process, or can be done as an interactive process. And I guess you're starting to see how this all slides in very nicely. So in terms of security, the signatures should be enforceable in the normal sense of UFCMA, or even for group signatures, you can even do with a weaker security requirement for the unforgeability, but we won't talk about that. What really is the issue is that the certificates need to be unfakeable, i.e. the adversary cannot make a new certificate, and this is sort of where this happens. The unfakeability is what tends to introduce the Q-type assumption. So basically what we're saying is that its adversary cannot make a new certificate, and to be more precise, I'm going to present the certificate unfakeability security game now. So this takes place between the certified signature challenger, which we've denoted here as CertSig, and the forger or faker, which we've denoted as F. So what CertSig first does is it runs some generation algorithm, and it generates some public parameters and its own secret key. It sends the public parameters to F. And after this, F can ask for new certificates to be issued. So the CertSig actually runs its keygen algorithm using its secret key, generates a verification key and certificate. We're going to ignore signing keys and all that for simplicity. And it sends the verification key and the certificate to F. And of course, F can make Q many of these queries, as many as F would like to have. Every time a new query is made, the verification key that is generated is added to the set of queried keys. And after all the queries have been made, F produces a tuple vk star, cert star, m star, sigma star, where cert should be a certificate on vk, and m star sigma star should be a signature under vk, message signature parent under vk. So in other words, F wins if vk star is not in queue, and verify pp vk cert star m star sigma star returns true. Now the real trick here is these cert stars. This is where a lot of the cert i's, this is where the problem comes. And to put it simply, most of the schemes that are there, the certified signature schemes, what they do is they use a Q-type assumption here. And basically what they do is they have an assumption which already provides them with a large number of certificates so that they can simulate all the certificates they need to. And when they're giving a new certificate, that becomes their Q+1 certificate, and that's a solution to their assumption, and that's how they win. So of course, then you get this reliance on this Q here, and that's where the Q-type assumption comes. And so basically what we do is we find a suitable certified signature, and we actually make it into one without a Q-type assumption. And to do this, we use our clever little trick. And the base idea is that we know that certificates are essentially a signature on the keys, right? Not more, not less. And we use a well-known trick from the literature, and this trick appears in various contexts and has a lot of applications, so it's a really neat trick. But we'll just recall very briefly what the trick is, and for more details, we'd have to refer to the literature. I don't have time to cover all of that. But essentially, a commitment of a signature and a proof of the validity of this of the signature contained within the commitment is actually equivalent to a signature. And like I said, we notice that these certificates are just signatures on the keys, which of course is not unexpected given how real certificates are issued in the real world with PKIs, where they simply issue a signature on your public key and some other information, right? So now that we see that that's just a signature and we have this trick, well, that's all we do. We just replace the certificate with a commitment and an ISIC proof of validity. Although this sounds quite trivial, it did take a bit of working out to figure out which scheme to use, which specific scheme to use, and how to actually do it in a slightly more intelligent way than just the very brute force methodology. So we did have to do a little bit of fiddling around here. But once we have this, we can now use tricks that are commonly associated with NISICs and commitments. In particular, when we're doing our proofs, we switch from commitments of certificates to random commitments, so commitments of random values. And of course, because these are no longer valid certificates, we need to adapt our NISIC proofs, and we use the trapdoor in the CRS to simulate the NISIC proofs. Now, having done that, we actually avoided having to compute any of the certificates, where we simply send these random commitments and the simulated proofs, and they work exactly as we desire. And then we're okay. And then once we have that, we don't need to actually simulate any certificates. We can then now correctly embed our challenge without needing a Q assumption. So we can just have a standard assumption. We embed it as our challenge correctly. And then we're done without having a Q assumption. And a very brief comparison. So I won't go into too much detail in this table, but this is an extract of our table from the paper. And you can actually look at that for more details on exactly this. And here I've ordered them by number of elements in the signature. Here you can see the Blasi and Poincheval is the shortest, with the longest being that of Libert, Peter, and Jung. And that's between 37 and 47 elements. So there's 10 elements difference between the largest and the smallest. And as you can see, ours are the second largest scheme. And the difference between, so the last two schemes both do not rely on Q-type assumptions. However, the difference is that the Libert, Peter, and Jung scheme requires structure preserving signatures. So their methodology is not generic, whereas ours is quite generic. So there is some scope for us to get smaller signature sizes if we come up with new clever primitives that are compactor or work better together, such that we can save some elements somewhere. But as you can see, I mean, we're not too far off from the Q-type schemes that were known, both by so the Blasi and Poincheval, and the adapted scheme of Jens Groth by Libert, Peter, and Jung, and my earlier work where I adapted the same scheme of Jens Groth to work in type 2 and type 3 pairings. We can see that we get to very similar numbers, and therefore we are quite competitive with the signature scheme. So, and again, this approach is fairly generic, so you can plug and play with other primitives, and hopefully it should give us some good results. So, just to sum up my talk now, we provided a generic construction of group signatures without Q assumptions. We showed how to convert one building block from a Q type to a standard assumption. And this conversion, of course, causes some small increase in the signatures, but of course it's still comparable to known schemes. The full version is available on IACR ePrint as report 858, year 2015. And of course, if you have any comments, questions, please feel free to contact me. Thank you very much.
Hi, I'm Vivek Arte, and I'm going to talk about incremental cryptography and incremental pseudorandom functions. This is joint work with Mihir Bellare and Louisa Khate. Consider a party that wants to compute a cryptographic function, say for message authentication, on a large document. It does so by applying the function to the document and generating the tag. This in general could be slow for large documents. Suppose the party now needs to edit the document in order to update it. If we use the function to generate the tag for the updated document from scratch, it would be slow and inefficient. This is problematic in today's age of big data, where one often deals with large documents that require real-time and frequent updates. Instead, we could use the property of incrementality, first introduced in 1995 by Bellare, Goldreich, and Goldwasser, to use the tag of the unedited document, and the editing details to generate an updated tag much faster than computing the tag from scratch. Incrementality has already been studied for different areas of cryptography, such as message authentication, authenticated encryption, collision-resistant hashing, digital signatures, deterministic public key encryption, and even program obfuscation. One basic area in which it has not been studied, however, is pseudorandom functions. We bridge this gap in our work. Why are incremental pseudorandom functions of interest? Adding incrementality to PRFs allows for improving the efficiency via the use of incremental functions in a broader range of applications, more specifically those that need pseudorandomness. Consider the application of key derivation, where an application holding a key k regularly uses its data to generate subkeys ki. This data may consist of a mix of static data, which stays constant, and dynamic data, which is different at each iteration. Using an incremental PRF will allow updating the key from ki to ki plus 1 faster than computing it from scratch. We now outline our contributions. We divide them into 3 parts, namely definitions, tools for modular design, and constructions. We introduce incremental pseudorandom functions and incremental function families. The syntax for these objects is nonce-based. We will see what this means in a bit. We provide security notions for our incremental function families. We first talk about incremental pseudorandomness, which is the extension of PRF security to the nonce-based and incremental settings. Then we cover incremental unforgeability, which is an extension of the basic security definition from Bellare et al. 95 and is used for incremental message authentication. Schemes can be considered for 2 scenarios. For single document schemes, security is guaranteed only when a single document is considered as being edited and updated. On the other hand, in multi-document schemes, security holds even when there are multiple documents with different file names or identities that are being edited simultaneously. We provide transforms that convert schemes secure only for single documents to schemes secure in the multi-document setting. Our first transform uses a pseudorandom function as an auxiliary tool, while the second one uses a variable length hash function. These transforms work for both incremental unforgeability and for incremental pseudorandomness. We then provide a transform that builds a single document IPRF scheme from an incremental hash function. This serves as an extension of the Carter-Wegman paradigm to the incremental setting. Our transform uses a symmetric encryption scheme in addition to the incremental hash functions we mentioned earlier. We then apply the previous transforms to build IPRFs based on various existing message authentication schemes, such as the PMAC, GMAC, XORMAC, and so on. The basic concept is to extract an incremental hash function from the message authentication scheme and use the IHTE transform to build an IPRF. Incremental cryptographic schemes sit on top of a non-cryptographic object called a document editing system. This describes the format of documents and the supported edit operations on them. The edit function is used to formalize the application of edit operations on the document. It takes a document, an operation code, some arguments, and returns an updated document D prime. The document D is a bit string that has a length that is a multiple of the block length. The operation codes and arguments are elements of a set that is specified by the document editing system. We now look at some examples of edit operations. We start with the replace operation, which replaces a block specified by its index number I with a block X. Another example is the insert operation. It inserts a block X at the ith position of the document. The final example we consider is the delete operation. As the name suggests, this operation deletes the ith block of the document. A document editing system is a tuple which contains the block length, the block space, which we assume to be the set of bit strings that have length equal to multiples of the block length, the set of edit operation codes, which stores the types of edit operations supported by the document editing system, the set of edit operation arguments, elements of which specify details of how the edit operation should act on the document, and the edit function, which takes the edit operation code, operation arguments, and the document and returns an updated document. We now start with a description of the three algorithms that are part of the definition of any incremental function family. A tagging algorithm takes a key, a nonce, the identity, and the document and produces a tag for the document. The update algorithm takes the key, a nonce, the identity, the document, the edit details, and the original tag and produces an updated tag for the updated document. The verification algorithm takes the key, the identity, the document, and the tag and returns a Boolean as to whether or not the verification succeeded. Note that the verification algorithm actually does not take a nonce. That is, verifying if the tag is valid does not require knowledge of the nonce used for tagging. An incremental function family is defined for a specific document editing system. It is a tuple which contains the key space, the nonce space, and output space, which are sets of allowed keys, allowed nonces, and allowed tags respectively. The tagging algorithm, update algorithm, and verification algorithm are also in the tuple, and we have looked at those already in some detail. Nonces were first introduced in the works of Roggeway and others in the early 2000s. Nonces are values that can be picked by the adversary, with only the requirement that the values picked must not repeat. Algorithms in nonce-based settings are deterministic, but they take the nonce as an input. Nonces can be used to capture both randomized and stateful algorithms. Security while using nonces guarantees that the security goal holds even when the adversary can pick non-repeating nonces arbitrarily. This precludes issues arising due to randomness failures. The benefit of using nonce-based definitions for PRFs is that they allow for the capture of more constructions, such as those based on the Carter-Wegman paradigm. This increases the applicability of these definitions. Nonces are widely used in practice and are an important component of Internet standards for authenticated encryption and TLS. We now take a look at correctness. Correctness is a functionality requirement, not a security requirement. The basic notion requires that the tags that are generated via legitimate sequences of the tagging and update algorithms must be accepted by the verification algorithm, even if the nonces are repeated. Consider a document represented here by a green list. Suppose we run the tagging algorithm on this document using a fixed key and ID and some nonce to generate a tag which is represented by the purple rectangle. Such a tag should successfully verify under the same key and ID and for a specific document. Next, consider running the update algorithm with the same key and ID and some nonce using this document and the previously generated tag and some edit operations. This will generate a new tag represented here by a darker purple rectangle. Correctness then requires that this updated tag successfully verifies under the fixed key and ID and for the document generated by applying the edit operations that were picked in the update step. There are more involved cases that will also need to be considered, and we account for them all via a game in our work. We now look at a stronger form of correctness that we introduce, namely strong correctness. This stronger definition requires a tag produced by the update algorithm on a document to exactly match the tag produced by the tagging algorithm on the updated document when using the same nonce. To unpack this a bit, consider a document D, and suppose we apply the tagging algorithm on this document using a key K, a nonce N prime, and a document identity ID to generate a tag T. Next, apply the update algorithm to generate the updated tag T. This algorithm will use the original document D, the previously generated tag T, the key K, a nonce N, and some edit operations. Let dnew denote the updated document that is generated by applying the edit operations to the document D. Strong correctness then requires that the tag that is generated by running the tagging algorithm on this document dnew using the same nonce as before, namely n, results in exactly the same tag. The benefit of having strong correctness is that it allows for proofs to drop the update algorithm altogether and simply replace it with an instance of the tagging algorithm that instead runs on the updated document. We define incremental PRF security of an incremental function family for a document editing system via a game played by an adversary. At a high level, the game checks if the adversary is able to distinguish between the output of an incremental PRF and the output of a random function after receiving tags for documents and updates of its choice. The game starts by picking a key at random from the key space and a random bit B. The game also picks a random function with the same domain and range as the IPRF. The adversary has access to 3 oracles, and its goal is to guess the random bit. The 3 oracles are the tag oracle, to which an adversary provides a nonce, identity, and document, and which then returns either the output of the IPRF for that combination of inputs with the picked key if B is 1, or the output of the random function if the bit B is 0. The second oracle is the update oracle, which takes a nonce, an identity, and edit operation details from the adversary, and returns the output generated via the IPRF update algorithm using the inputs provided and the current document and tag values stored by the game when B is 1, or the output of the random function using the given nonce, identity, and the updated document when B is 0. The third oracle is the verify oracle, which takes as input the identity, the document, a tag, and in the case where B equals 1, returns the output of the verification algorithm on these inputs if the queried document is not one that has been queried in previous tag and update oracle queries. If B is 0, then it always returns false. As a standard in nonce-based frameworks, we do not allow the adversary to repeat nonces between queries. Further, the adversary is required to make a tag query for a given identity before making any update queries for that identity. The advantage of an adversary in this case is the standard distinguishing advantage adapted for bit guessing games. Informally, we can say that a scheme is IPRF secure if the advantage of any practical adversary is small. The notion of incremental unforgeability, or IUF security, is based on the notion of basic security from the 1995 work of Bellari et al. And extends it to the nonce-based setting. As for IPRF security, we define IUF security of an incremental function family for a document editing system via a game played by an adversary. At a high level, the game checks if the adversary is able to forge a tag that successfully verifies for a new document after receiving tags for documents and updates of its choice. As before, the game picks a key at random from the key space, and the adversary has access to 3 oracles. The goal of the adversary is to set the win flag to true, which corresponds to a valid forgery. As before, the 3 oracles are the tag oracle, the update oracle, and the verify oracle. If the verification returns true, the adversary has achieved its goal and completed a forgery, and therefore the win flag is set to true. The advantage of an adversary is defined as the probability that the adversary wins this game. Informally, we can say that a scheme is IUF secure if the advantage of any practical adversary is small. Why do we need to consider updates separately? The adversary may have access to previous versions of documents and their tags. The adversary may also be able to issue edit commands to existing documents and obtain new incremental signatures. This may allow for attacks that break schemes that cannot be broken when restricted to not using the incremental update algorithm. However, as mentioned earlier, updates can be dropped in the case where the scheme under consideration satisfies strong correctness. In this case, update oracle calls can be replaced with tag oracle calls, and the argument to the tag oracle call is then changed to the updated document. We now discuss relations between pseudorandomness and unforgeability. In the standard definition of IPRF security and unforgeability, it has been shown that PRF security implies UF security. This standard definition is not nonce-based, and it also does not consider incrementality. More recently, there have been definitions of nonce-based PRFs and nonce-based MACs. Perrin and Serron have shown in 2016 that for these nonce-based definitions, there is a separation between PRF security and UF security. Note that these definitions are not for the incremental setting. Moving on to our work, we show that our PRF security notion implies our IUF security notion. An informal theorem statement is as follows, which shows that there isn't any security loss occurring during the reduction. The consequence of this implication is that once we show IPRF security, we can immediately proceed to use the scheme to perform message authentication. Note that achieving this implication was a motivation behind including the verification oracle in our IPRF game, which makes the definition differ from non-incremental versions of PRF security. The single document setting, as we have seen, is the use case where we consider that there is only a single document on which tagging and updates are being performed. This setting was the one considered in the original work on incremental cryptography by Bellari et al. In 1994. On the other hand, the multi-document setting allows for consideration of multiple documents with different identities and maintains security in such a scenario. The follow-up work of Bellari et al. In 1995 was the first to consider both these settings separately. However, they considered schemes independently for both settings. We first show that the multi-document setting is strictly stronger than the single document setting by means of an example scheme which is secure in the single document setting but not in the multi-document setting. In real life, it is more reasonable to assume that there are multiple documents that need to be considered by a user, and therefore the multi-document setting is more relevant in practice. At the same time, the single document setting tends to be easier to achieve due to the lack of document identities to be considered. We construct two generic transforms that use certain auxiliary tools to convert an incremental function family secure in the single document setting into an incremental function family secure in the multi-document setting. The first transform, which we denote by STM1, uses a non-incremental PRF to do so. However, the security reduction in this case is not tight. We therefore provide a second transform, which we denote by STM2, that uses a variable length hash function and provides a tight reduction of security. These transforms allow us to focus on building single document schemes, since we can then use the transform to get multi-document schemes. We now have a look at the transform STM1. We use IFMD to denote the multi-document incremental function family, while the single document incremental function family is denoted by IFSD. At a high level, the transform proceeds by generating a different key for each identity using the PRF, and then using this different key for each different document identity in the single document scheme. Let us look at the resulting algorithms for the tagging, update, and verify algorithms. In all these cases, the components are the corresponding algorithms from the single document scheme and the PRF. Let's focus now on the tagging algorithm. The multi-document algorithm takes the key and the identity, gives those as input to the PRF, and generates a key corresponding to each identity. This new key is fed along with the remaining inputs to the multi-document algorithm to the single document algorithm, and the output is given as the output of the multi-document algorithm. Both the update and verify algorithms proceed in analogous fashion, and therefore we skip over their details. The theorem we prove in our work bounds the advantage of an adversary against the multi-document scheme as follows. It is easy to see that the reduction succeeds and the multi-document scheme is secure. A similar result also holds for IUF security. Note, however, that the inequality contains a multiplicative security loss corresponding to the number of distinct document identities queried. As a result, this reduction is not tight. Our quest for a tight reduction leads us to our second single document to multi-document transform. As before, we use IFMD to denote the multi-document scheme, and we use IFSD to denote the single document scheme. The variable output length hash function is denoted by H. At a high level, the transform proceeds by using a hash of the identity and nonce to generate an updated nonce n prime. Then, the scheme prefixes a hash of the identity to the document to create an updated document D prime. The scheme then uses this updated nonce and updated document in the single document scheme. The update algorithm for the most part runs analogously. However, note that the prefixing of an additional block to the document means that the edit operation details need to be tweaked before using in the single document update algorithm. We denote this by an operation translate function, which takes as input the arguments and returns the tweaked arguments as output. For example, if the operation was to replace the ith block with x, it would get tweaked to replacing the I plus 1th block with X. All these inputs are then given to the single document algorithm, and the resulting output is set as the output of the multi-document algorithm. The verify algorithm proceeds analogously to the tagging algorithm, and so we skip the details. The theorem we prove in our work bounds the advantage of an adversary against the multi-document scheme as follows. It is easy to see that the reduction succeeds and the multi-document scheme is secure. A similar result also holds for IUF security, and we also note that our reduction is now tight. Moving on in our modular design journey, we now look at the Carter-Wegman paradigm. This paradigm, introduced in 1981, is a well-known technique used to construct a message authentication scheme using an almost universal hash function and a cryptographic masking function. General construction passes the message through the hash function and then masks the hash using the key and the nonce to generate the tag. Message authentication schemes using the Carter-Wegman paradigm are very popular in practice due to their speed and efficiency. Examples of such schemes include the UMAC, the VMAC, and the GMAC. The UF security of the MAC follows as a result of the almost universality of the underlying hash function and the security of the cryptographic masking function. This could be PRF security if the mask is a PRF, or it could be INDCPA if the mask is an encryption scheme, and so on. We now proceed to look at our extension of the Carter-Wegman paradigm, which we call the incremental hash then encrypt transform. Now, IHTE transform uses as building blocks an incremental hash function IHF, a symmetric encryption scheme SE, and a key distribution function KDF. The symmetric encryption scheme must follow the NDE2 syntax of Bellare, Ng, and Tachman 2019. The important point here is that the decryption algorithm should not need to take the nonce as input in order to decrypt. Further, we assume that the incremental hash function is incremental for the replace operation. Our transform extends the incrementality of the hash function to the resulting incremental function family, while also achieving IPRF security in the single document setting. We now look at how the tagging and update algorithms work, while we skip the description of the verification algorithm as before. We start with the key derivation function. This block actually occurs within each algorithm, but for ease of viewing, we pull it out and assume the tagging, update, and verification algorithms have access to both the derived keys. The KDF captures various design choices for the keys, such as keeping the keys for two schemes the same or picking them independently at random, among others. Let's now look at the tagging algorithm. The algorithm takes a number of inputs like the key, the nonce, and the document, just as per the usual incremental function family syntax. Note that since we are now in the single document setting, the identity is considered to be trivial and we can ignore it. The first step is to run the key distribution function in order to generate the keys, which we assume is already done. We then use the incremental hash function along with the generated IHF key to hash the document and generate a hash value H. The document then uses the symmetric encryption algorithm with the symmetric encryption key, the nonce, and the hash value H to generate the tag. We now turn to the update algorithm. The first step there is to use the input of the original tag and use the symmetric decryption algorithm to extract the original hash value. This decryption follows the NDE2 syntax as we mentioned earlier. Next, the original hash value is input along with the original document and the edit details to the update algorithm of the incremental hash function. This returns an updated hash value H prime. Finally, this updated hash value is used along with the nonce and the symmetric encryption key to construct the updated tag. We show that we can achieve IPRF security of this construction if we have computational almost universality of the underlying incremental hash function and AE2 security of the underlying symmetric encryption scheme. Computational almost universality was formalized by Bellare in 2015 and is the computational relaxation of the almost universality notion we mentioned earlier. AE2 security is a notion of security for NDE2 schemes that is also defined in Bellare, Ng, and Tachman 2019. We now look at some of the existing message authentication schemes used in the real world and study how to use them to construct incremental function families for the replace operation. We first see that after bringing the PMAC and PMAC1 schemes into our syntax, we directly obtain IPRF security for them, and therefore IUF security follows immediately. For a number of constructions, namely the XOR MAC, the GMAC, the Poly 1305 AES, and PWC, the natural expression in our syntax gives us IUF security but not IPRF security. This is because these schemes require the nonce to be part of the tag, and therefore achieving pseudo-randomness is not possible. To get IPRF security, we instead extract an incremental hash function from each of these and then use a IHT transform. Finally, we note that the PMAC plus and ZMAC schemes do not achieve incrementality on being naturally transformed into our framework. However, we are still able to extract an incremental hash function from these constructions, and we use that with the IHT transform to get IPRF security. So to summarize, we define incremental function families within a non-space framework and introduce strong correctness as a property to reduce proof complexity. We define two notions of security, IPRF and IUF, for these incremental function families. We showed that IPRF security implies IUF security. We constructed two transforms that go from schemes that are secure in the single document setting to schemes that are secure in the multi-document setting. We also constructed a transform that takes an incremental hash function and returns a scheme that is IPRF secure for single documents for the replace operation. We extract incremental hash functions from various existing message authentication schemes and use them to build secure IPRFs for the replace operation.
The segment Non-Interactive Zero-Knowledge Proofs covers dual mode NIZ case, possibility and impossibility results for property transfer by Vivek Arte and Mihir Bellare on a black box extension of a non-interactive zero-knowledge proof system for secret equality by Kosuke Emasta, Mehdi Tibochi, and Masayuki Abe.
Hi, I'm Vivek Arte, and I'm going to talk about dual mode non-interactive zero knowledge and property transfer. This is joint work with Mihir Bellare. We start by recalling non-interactive proof systems, which were first constructed by Blum, Feldman, and Micali in 1988 in the Common Reference String model. In the Common Reference String model, there are two parties called the prover and the verifier, and there's assumed to be a trusted setup algorithm that generates a common reference string and sends it to both parties. A relation is a function that takes as input the common reference string, a statement X, a witness W, and returns either true or false. We are interested in NP relations, which is when the function R is polynomial time and the size of the witness is polynomially bounded in the size of the statement and the size of the common reference string. The language associated with this relation and the common reference string is defined as the set of all statements that have a witness satisfying the relation. As part of the proof system, the prover is supposed to have a statement X and a witness W such that the relation on the CRS X and W is true. The goal of the prover then is to convince the verifier that the statement X is in the language. In order to do this, the prover runs the proof generation algorithm and sends the generated proof to the verifier along with the statement X the proof corresponds to. The verifier then runs the verification algorithm and uses it to decide whether the proof is valid or not. That is, if the verification algorithm outputs true, the verifier is convinced that the proof is valid, otherwise not. We require proof systems to be complete. That is, proofs that are generated by the proof generation algorithm for a statement in the language must always lead to the verification algorithm returning true for the same statement and proof. Beyond completeness, there are other properties of proof systems that are often aimed for in the literature. The soundness property requires it to be hard for a polynomial time adversary to construct a proof for a statement that is not in the language, such that the verification algorithm accepts the statement proof pair. There are different variants of soundness existing in the literature. We will in particular look in closer detail at two notions that we will call SNDE and SNDP. The extractability property is also known as the proof of knowledge property. It requires that if the prover is able to produce a valid proof for a statement, then there is an extractor algorithm that can obtain the witness from the information the adversary has access to. The extractor is given access to a trapdoor that underlies the common reference string. The witness indistinguishability property guarantees that if there are two witnesses for a statement, It is hard for an adversary to be able to tell which witness was used in order to generate the proof. Finally, the zero knowledge property guarantees that a proof generated for a statement in the language reveals no information about the witness for that statement. The concept of dual mode proof systems was first introduced in the 2006 work of Groth, Ostrovsky, and Sahai. In this technique, there are two proof systems, Pi0 and Pi1. The two CRS generation algorithms generate common reference strings which are computationally indistinguishable from each other. Both proof systems have proof generation and verification algorithms which are identical to their counterparts in the other proof system. So what is the benefit of such a pair of proof systems? Groth, Ostrovsky, and Sahai use the perfect soundness of one mode and the computational indistinguishability of the common reference strings in order to prove computational soundness of the other mode. This computational soundness, coupled with the perfect zero knowledge of this other mode, led to the construction of the first perfect zero knowledge argument system, a major open question of the time. We now look at some of the other papers that consider dual mode proof systems and look at the requirements they place on the individual modes. A common thread in all these works is that each mode has some specific requirement to be met. For example, one of soundness or extractability in one mode, and one of zero knowledge or witness indistinguishability in the other. For example, the work of Albrecht et al., in which dual mode systems are used to build multilinear maps, has a perfect soundness and extractability requirement in mode 0, and a perfect zero knowledge and witness indistinguishability requirement in mode 1. The Groth, Ostrovsky, Sahai paper we saw earlier has perfect soundness requirement for mode 0 and a perfect zero knowledge requirement for mode 1. The work of Belenki et al. Is used for constructing anonymous credentials. It requires perfect soundness in mode 0 and perfect witness indistinguishability in mode 1. We now introduce the terminology of transference. We have a pair of proof systems, Pi0 and Pi1, that are dual mode proof systems. That is, the CRS generation algorithms generate common reference strings that are computationally indistinguishable. If one proof system, say Pi0, satisfies a property P, then we can use that along with the computational indistinguishability of the common reference strings to claim that the other proof system, that is Pi1, satisfies the computational analog of property P. We say that the property P transfers if this claim holds. The purpose and applications of prior work depend on the transference of different properties between the modes of the proof systems. Therefore, we ask the question, which properties transfer? We are interested in studying transference for a number of different properties like zero knowledge, witness indistinguishability, extractability, and soundness. We now take a look at our contributions. We define dual mode proof systems so as to only have the CRS indistinguishability requirement and no additional requirements on the individual modes. We call this requirement mode indistinguishability. We formulate the question of transference and ask which properties transfer. We prove some negative results. We show via an explicit counterexample that the SNDP notion of soundness does not transfer between the two modes of a dual mode proof system. We also show, again via an explicit counterexample, a separation between the SNDE and SNDP notions of soundness. This result holds for regular proof systems. Both our counterexamples are based on the hardness of the decisional Diffie-Hellman assumption. We then turn to positive results. We provide an abstraction of property specifications and then state and prove a transfer theorem. This allows us to capture all the positive results simultaneously with a single proof. As a result, we are able to show that the standard definitions of zero knowledge, witness indistinguishability, and extractability do transfer. Let's now look at the syntax and definition of dual mode proof systems. The syntax of dual mode proof systems is very similar to those of regular proof systems. Just as in the regular case, there are three algorithms corresponding to CRS generation, proof generation, and verification. The CRS generation algorithm syntax is different for dual mode proof systems. In this case, it takes an additional bit as input, mu, which is used to denote the mode of the induced proof system. The dual mode CRS generation algorithm thus induces two non-interactive proof systems depending on the choice of the bit mu. We emphasize that these induced proof systems are just regular non-interactive proof systems and can satisfy properties just as normal. The only requirement we make of our dual mode proof systems is that the common reference strings generated in these two modes be computationally indistinguishable. We call this property mode indistinguishability, and it is the only property that we will mandate for our dual mode proof systems. We now move on to transference. As we have seen, transference refers to the scenario where we can conclude the satisfaction of the computational analog of a property P in one mode based on the satisfaction of the property P in the other mode and the mode indistinguishability of the dual mode proof system. Some examples of properties of interest are soundness, zero knowledge, witness indistinguishability, and extractability. We will see that a property P transfers if it can be specified in polynomial time. We turn now to negative results. We first stop to take a look at the property of soundness, which is defined with respect to a relation R. At a high level, for soundness to hold, the adversary must not be able to return a statement proof pair such that the statement is not in the language, but the verification algorithm returns true. There are two variants of soundness depending on whether the definition is penalizing or exclusionary. This distinction between penalty style and exclusion style definitions was first considered in 2015 by Bellare, Hofheinz, and Kiltz in the context of public key encryption and key encapsulation mechanisms. These two definitions differ in the kinds of queries the adversary is allowed to make. The penalty style definition, which we denote by SNDP, makes no restrictions on the polynomial time adversary. Instead, it includes in its win condition a check of the language membership for the statement in the query, which is highlighted in blue. This prevents the adversary from winning using a query with a statement in the language. Note that the membership test will not be efficient for languages in NP, which are the languages of interest to us. In the exclusion style definitions, which we denote by SNDE, the adversary is restricted to almost never make queries in which the statement is not in the language. We formalize this by requiring the adversary to belong to a class of membership-conscious adversaries. A membership-conscious adversary is one which picks a statement belonging to the language with negligible probability. In the described game, this corresponds to the adversary setting the bad variable to true with negligible probability, as is highlighted in green. The win condition for an adversary in this case, as a result, is simply a check for whether the verification algorithm accepts the proof as valid. We now turn to the question of which of these definitions are good for applications. We notice that the penalty style definition is more application enabling and useful for applications, while the exclusion style definition is less so. We consider as a canonical application the use of non-interactive zero knowledge to construct digital signatures, as was first done by Bellare and Goldwasser in 1990. We see that the SNDP style definitions allow us to construct digital signatures, while the proof doesn't go through in the case of the SNDE style definitions. We now describe how the two relations of soundness compare to each other. It is easy to see that the penalty style definition automatically implies the exclusion style definition. This is because an adversary that attacks the SNDE notion will also attack the SNDP notion with only a negligibly smaller probability. On the other hand, the reverse implication does not hold. That is, SNDE does not imply SNDP. We show this separation via a counterexample. More specifically, we construct a non-interactive proof system and a relation R, such that the proof system satisfies the exclusion definition of soundness, but at the same time, it does not satisfy the penalty definition of soundness. This counterexample is based on the assumption that there exists a group generator such that the decisional Diffie-Hellman problem is hard to solve in that group. This shows the SNDE definition is strictly weaker than the SNDP definition. We now show that for dual mode proof systems, the penalty style definition of soundness does not transfer. The intuition is that this property fails to transfer because transference requires a reduction adversary to test for membership in the language. As we have mentioned, languages of interest are in NP, which means that membership tests would be inefficient. We show that there exists a dual mode proof system dpi and a relation R such that dpi is mode indistinguishable and one induced mode of dpi is SNDP for the relation, but the other induced mode for dpi is not SNDP for the relation. We show this by means of an explicit counterexample that is again based on the hardness of the decisional Diffie-Hellman assumption. The dual mode CRS generation algorithm generates the common reference string in two different ways based on the value of mu. From this, it is easy to see that the mode indistinguishability follows directly from the DDH assumption in the group. Further, we define the relation in such a way that the language consists of all group elements except G raised to AB. The proof generation algorithm we construct is trivial, while the verification algorithm we construct verifies all statements X in the group and returns true for all these statements. As a result, in order to break soundness, the adversary needs only to pick X equals G raised to AB. We now look at the attack against SNDP when mu equals 0. Notice here that the CRS itself contains G raised to AB. Therefore, the adversary can simply return that value picked from the common reference string along with a trivial proof and then break soundness with probability 1. When mu equals 1, we show that we can reduce the SNDP property to the DDH assumption in the group. We turn now to positive results. First, we want to show that SNDE transfers. So here we are given that one mode of the dual mode proof system satisfies SNDE soundness, and we also know that the dual mode system satisfies mode indistinguishability. If it was the case that the other mode did not satisfy SNDE soundness, this could be used as a distinguishing test for mode indistinguishability. It's important to note that this depends on the polynomial time nature of the SNDE game. If that were not the case, a distinguishing test based on the SNDE game would not be polynomial time and therefore would not be able to be run by the distinguishing adversary. We would prefer not to have to prove individually for each property of interest whether that particular property transfers. Therefore, we create the abstraction of a property specification. A property specification captures the game that corresponds to a particular property P. We do note that there are slight differences to the property specification based on whether the game problem is of a decision type or a search type. The property specification absorbs all of the oracles of the properties game into its single oracle and maintains state in such a way that it can perfectly simulate the property game. As a result, we are able to construct property specifications that perfectly match the behavior of their target properties game. The transfer theorem states that a property specification that runs in polynomial time corresponds to a property that transfers. We see that the property specifications for zero knowledge, witness indistinguishability, extractability, and the exclusion form of soundness all have polynomial time property specifications. However, the property specification for SNDP is not polynomial time. This is because of the win condition. The membership test in there is not polynomial time for languages in NP. Thus far, we have discussed everything in the common reference string model. The designated verifier model is set up in such a way that only a specific verifier will be able to verify the proof. This is captured by having a secret verification key that is given only to the verifier. The designated prover model, meanwhile, is set up such that only a specific prover will be able to generate proofs. This is done by having a secret proving key that is given only to the prover. The pre-processing model has secret information handed to both the prover and the verifiers. This is captured by using both the proving and verification keys simultaneously. We note that all results discussed here work in these other models as well. So to summarize, we have defined dual mode proof systems with only the mode indistinguishability requirement. We also define what it means for a property to transfer, and we ask which properties transfer. We prove that SNDP, the penalty style definition of soundness, does not transfer via an explicit counter example based on the hardness of the decisional Diffie-Hellman assumption. We prove via a general framework that many properties like zero knowledge, witness indistinguishability, extractability, and the exclusion form of soundness do transfer. We also show that the penalty style definition of soundness is a strictly stronger notion than the exclusion style definition of soundness. The main takeaways are that we must be careful while using dual mode systems and applications. We must check that we actually do get the properties we require from the induced proof systems and not expect it to be implicit due to transference.
Hello everyone. I am Kyosuke Yamashita, a PhD student in Kyoto University and a research assistant in AISD, Japan. I will be talking about the problem of expanding a language class that NIZK proves in a black box manner. This is a joint work with my supervisors, Mehdi Tibusi and Masayuki Abe, NTT, Japan. First of all, let me explain what type of research this work is. This is so-called black box construction. So, we consider if we can construct a primitive Q based on primitive P in a black box manner. More concretely, we are given an oracle that implements a primitive P. Then, we consider if we can construct Q by using this oracle. Because P is given as an oracle, we do not care how P is implemented, and that's why it is called black box. If such a secure construction exists, then we say there exists a black box construction of Q based on P. Otherwise, we say Q is separated from P. Black box work was formalized by Impagliazzo and Rudihi in 1989, who showed a black box separation between key agreement and one-way function. Since then, a lot of results have been proposed. Let me explain which primitive we consider in this work. We treat non-interactive zero-knowledge proof system, NIZK for short. An NIZK is a protocol between two parties, a prover P and a verifier V. They share a common reference string and a statement X of an NP language L. Only the prover has a witness of X and wants to prove X indeed belongs to L without revealing the witness. So, the prover creates a proof pi and sends it to verifier. Then, verifier checks the validity of the proof. An NIZK has two security properties. One is the soundness, which guarantees that it is impossible to create a proof on a false statement. The other is zero-knowledgeness, which guarantees pi does not leak anything about the witness. NIZK is one of the most central primitive in cryptography, and it has a lot of applications such as blockchain. In this work, we will consider the problem of expanding a language class that NIZK prove in a black box manner. Roughly speaking, we consider if we can construct a stronger NIZK based on weaker NIZK in a black box manner. Here, weak and strong are in terms of languages they prove. Such a black box language extension was initiated by Abe et al. In PKC 2020. They showed two negative results. First, given NIZKs for languages L1 and L2 respectively, it is impossible to construct an NIZK for the language L1 or L2. Furthermore, even though given NIZKs are simulation sound, it is impossible to construct an SSNIZK for the language L1 and L2. It is important to note that a standard NIZK for L1 and L2 can be trivially constructed by running given NIZKs sequentially. Actually, this kind of languages are seen in a lot of applications such as electric voting or blockchain. So, the motivation behind the black box language extension is if we can construct a general framework for these applications. The PKC paper covers a wide class of languages, but there exists another class that this work does not cover. That is a language which includes witness relation, something like this. It says x1 belongs to L1, x2 belongs to L2, and some binary relation holds among W1 and W2. Here, any binary relation will do, such as equality or greater than. Among them, NIZKs for witness equality are used in a lot of applications. For instance, the well-known Nawo-Young construction uses an NIZK, which proves a plaintext behind two different ciphertexts are the same. In blockchain, an NIZK for witness relation is used to realize contingent payment, which guarantees fair trade. So, NIZKs for witness equalities are important in cryptography, and it is not covered by the previous work. So, in this work, we will focus on NIZKs for witness equality. In particular, we consider the Nawo-Young construction, and our result is as the following. Given a CPA PKE and an NIZK for the following single ciphertext language, LCPA, then there is no fully black box construction of an NIZK for the following plaintext equality language, LEQ. Here, LCPA is a set of ciphertext C and a public key PK, where C is a correct ciphertext under PK. LCPA is a set of ciphertexts and public keys, where C1 is a correct ciphertext under PK1, C2 is a correct ciphertext under PK2, and C1 and C2 are the encryption of the same plaintext M. It is important to note that this LEQ is not covered by the previous work. In the context of the previous work, they only rule out languages something like this. It says C1 is a correct ciphertext under PK1 and C2 is a correct ciphertext under PK2. However, C1 and C2 are kind of separated, so there is no guarantee that M1 and M2 are the same. Okay, in what follows, I will explain technical aspects of this work. Because we are considering a black box construction, we should introduce oracles that implement underlying primitives. As a CPA-PK oracle, we use the oracle introduced by Gardner et al. It consists of several interfaces, and the most important interface is the encryption interface, which takes a public key, a message, and a randomness R as input and outputs a ciphertext. Actually, this interface is implemented by a random injection. Then, we introduce an oracle that almost directly implements an NIZK for the single ciphertext language. The oracle ZK consists of these interfaces: CRS generator, prover, verifier, and prover simulator. Here, the most important interface is the prover, which takes a CRS, a ciphertext, a public key, a message, and a randomness, and outputs a proof pi. Actually, this interface is implemented by a random injection as well. We showed that ZK constitutes an NIZK for the single ciphertext language, but I do not explain it in detail here. Now, let me sketch the proof of our main result. First, we assume that there exists a black box construction M over proof system for LEQ that is zero knowledge. Then, we construct an adversary that breaks the soundness of M in the soundness game. The game is done between a challenger and an adversary who have oracle access to them. First, the challenger runs the CRS generator algorithm to obtain a CRS and sends it to the adversary. Then, the adversary picks a false statement, creates a proof pi hat on it, and sends them back to the challenger. Then, the challenger runs the verification algorithm. If this proof is accepted, then the adversary wins the game. It means the adversary breaks the soundness of M. Now, let me explain what the adversary do in this part. Here are some important observations for the adversary. Because the adversary has oracle access, it can simulate the prover algorithm inside. When the algorithm makes a query, it is actually made by the adversary. So, the adversary can control the query. Suppose the adversary is given a query X. Then, it can swap the query to another query X prime and return such a swapped answer to the algorithm. Because the encryption interface and the prover interface are implemented by random functions, respectively, this algorithm cannot detect such a swapping. By following these observations, the adversary forges a proof on a false statement. The adversary creates a false statement. It generates two ciphertexts C1 and C2, which are encryption of the same plaintext M under different public keys. Then, the adversary also generates another ciphertext C1 prime, which is an encryption of another plaintext M prime. So, this is a correct statement of LEQ, but this is not. Then, the adversary runs the prover algorithm on the false statement and do the following. Suppose the prover algorithm makes this query. Because M is not a correct plain text of C1 prime, this query should result in bot. So the adversary swaps the query so that it contains correct plain text M prime. Then, because M prime is a correct plain text of C1 prime, it should result other than bot. So the adversary returns this proof pi to the prover. The adversary repeats this until the prover outputs a proof pi. In next slide, let me explain why such a proof passes the verification. So roughly speaking, we can say the prover algorithm runs under other correct oracles O prime and CK prime. Let me explain about it. The left-hand side tables represent original oracles, and right-hand side represent swapped oracles. For instance, the prover interface assigns a proof pi to this query, assigns bot to this query. Of course, they are based on the result of the encryption interface. Then, because they are implemented by random injections respectively, there must be another oracle that swaps these entries. So, in other words, the prover algorithm outputs a correct proof under these swapped oracles. Because the proof is correct under these oracles, the challenger should accept such a proof, and the adversary wins the soundness game. As a conclusion, we showed that there is no fully black box construction of an NIZK for the plain text equality language based on NIZK for the single ciphertext language. This result suggests that if we want to construct an NIZK for witness equality, we should rely on certain properties such as algebraic structures. As a future work, it remains to consider other binary relations such as range proof. I think it is also interesting to consider the case where the underlying NIZK is more specific, such as commit and proof NIZK or quasi-adaptive NIZK. Okay, that's all for me. Thank you for watching my video.